Okay. So what exactly do we want to start with? Do we want to start with going over the exam 3 practice problems, or do we want to, are there any things you want me to address beforehand, or do we want to talk about beforehand? Like, I don't know, if you want to talk about symbol tables and binary trees,
We
or if
can
you
uh we can go over the practice problems.
practice problems, like exam 3
Yeah,
practice. Okay. Is that cool with everyone?
yeah. And I
Yeah.
think there were a
Good
few
with
of the
that.
traces that I kind of want to look at.
Okay. Sounds good. Okay, the first question, consider the following scenario. You need to store a record for each of the top 1,000 teams that participated in a machine learning competition in order to be able to look up which team placed in a specific place. Would it make more sense to use an array or a symbol table for this problem? Explain. So, looking at this, we have a record of each 1,000 teams, so we have a fixed number of teams. And we want to have some kind of organization to them. And it's asking us whether we want to use an array or a symbol table. And some of the options: A, an array will probably be better. It will be faster and more efficient in storage. B, an array will probably be better. It will allow the team record type to be stored properly. C, a symbol table will probably be better. It will provide more flexibility. Or D, a symbol table will probably be better. It will be more efficient in storage. Now, thinking about this, what is our goal? Our goal is only to look up a team. So we want to find some object based on what information? Well, based on what place they were in. So just off of that description, what do you think would be best? Do you think, any
I
guesses?
think we can eliminate A easily.
Well, without actually looking at the problems, what do you think would be better, an array or a symbol table? And why do you think
A
that?
symbol table.
You think a symbol table? Okay. Is there any reason why, or I want to know what your reasoning behind that is?
Doesn't allow for like easier access. That way you don't have to loop through the entire array. In some ways.
Okay. So the idea is that a symbol table will let you not have to loop through something. Now, I can see that, but what if we were to sort the array in order from first place to last place? What do you think then? Do you think a symbol table is still better, or do you think an array?
Yeah, I think a symbol table would still be better.
Okay.
Because isn't every time you call put, it puts it in some order? Or I'm
Uh,
probably thinking of linear probing.
hash
No, I'm probably thinking
tables,
of that.
yeah, symbol tables specifically don't necessarily need to have an order, but rather a way to get and put something based on a key. So this is essentially a symbol table definition. You have put, get, delete, contains, checking whether or not it's empty, size, and keys. This doesn't necessarily say anything about the order. We could be sorting things in no order. We could be sorting it in greatest to least. We could be storing it in any way. We don't know. And if you remember, like was it a max heap that was? I don't think heaps are in this, right? Unless I'm.
I think heaps was there in the trees. Or actually no.
Oh,
No, that is tree.
there's an ordered symbol table, which might be able to do what we were looking for. But specifically, we're looking at a symbol table, right? So we're going to assume this is what's defined for us. And knowing that we don't have any order, we don't assume any order, and knowing that we have the ability, or yeah, I'm trying how best to word this. Both could be used in this situation. Let's say our key in this case would be the place that they were in. Our key could be the word first, it could be a number first, or like a number 0, 1 through etc. An array, our key in this example would just be a number. It would have to be the index of the place. And in this situation, an array would be better because a hash table, or not a hash table, sorry, a symbol table infers that you might need something more than just an index, something that is not in order from 0 or 1 to some number, some order that is not linear, and maybe something that doesn't fill every gap, if that makes sense. So like in an array, in this situation, I would argue would be better because if we just kept it sorted, we don't have to declare extra space if we were using a hash map. We don't have to take additional time to search for the object if we were using like a binary tree. And the actual lookup time arguably could be the same, if not better than the symbol table. As in the symbol table, you may have to hash things. In this situation, you just use the number we're given. If we're saying first place, first minus 1 is 0, therefore it's index 0. Does that kind of make sense?
I mean, I just thought about an array of objects, and the teams are the objects, and then you would have like a variable rank, or you could have like I don't know, other variables like wins or losses, and then you would sort it according to those variables.
Now, that idea is kind of similar. If you have an array of objects and you wanted to sort that based on some property they have, that is achievable without actually changing the data structure. So typically when you're using like libraries in Java, if you tell it, hey, sort it, use a sum sorting algorithm on this data, and you're not just sorting numbers, they will ask you for something called a comparator. A comparator essentially says, okay, given A and B, give me a -1, a 0, or a 1, depending on where I should put it. And so you could sort by rank, name, address. I mean, at the end of the day, it doesn't matter what you want to sort it by. So therefore, an array or a symbol table wouldn't really matter in that. The array would still work the same in comparison to a symbol table. Now, I do know that if you were using a symbol table for, let's say your key was a string, if you wanted to say first place, if you stored whoever's in first place at that key, then it could refer to, let's say, the teammate, the one that won or whatnot. Or if you wanted to have a key that's like most wins, that key could also correspond to that team. So you could have duplicate values. However, the trade-off there is you're probably using more memory, and you're probably not utilizing the amount of space that would be required. You're probably also going to run into the collisions problem, where like you may have to use a linear hash table or a binary search tree or a some kind of other data structure on top of an array. Does that kind of make sense?
Yeah, it does. And which answer are we leaning towards here?
Knowing that an array would probably be better, then we're probably going to go with A or B. With C or D, let's first look. A symbol table will probably be better. It will provide more flexibility. Arguably, flexibility, yes. However, like, if you're only looking to rank a team based on their, like, what place they got, then it shouldn't really matter about flexibility, if that makes sense. The symbol table will probably be better. It will be more efficient in storage. That is not correct. It will probably have to allocate more storage space or end up being more data to hold in general. So for A or B, an array will be probably better. It will be faster and more efficient in storage. I would argue we'd want to be careful here. It's not necessarily always faster. I mean, it will be the same, if not better, as a symbol table. However, doesn't mean that it'll be faster every single time. Because, yeah, it depends on if you're comparing big O or growth function. It really depends on the situation. So I would be careful with this wording and be more efficient in storage. This, however, is true. This will be more efficient in storage. A binary tree has to allocate 2 pointers for every, or space for 2 pointers for every node. Therefore, you're essentially storing 2 numbers for every number, or 2 long ints for every node. So technically, it's not as efficient in storage. And then hash tables, depending on the implementation, you may either be using an array or you may end up allocating more space. For example, in the linear probing one, that one ends up allocating more space as it's needed. So B, it will allow the team record type to be stored properly. Now that's also arguable. I would say I feel like this would be a weird answer. I feel like A would probably be the best out of these, if not C.
I was going over this with Sai yesterday. I think we chose C.
Yeah, I think C is, if we don't really care as much about storage, and because they're arguing for saying arrays are faster, then I would say A is too ambiguous. They're making claims that aren't actually true, because this isn't always true. Therefore, I would go with the safer answer, which is C, since providing more flexibility is true. And B just doesn't make much sense as an argument. It allows the team record type to be stored properly. That means nothing to us. Right? Sure, somebody might interpret this as something, but I feel like this means nothing to us in the terms of the problem, like what it's asking us. And this is just false. So yeah, I would say C is probably the best bet, even though I would argue an array could be better. At the end of the day, I guess a symbol table could be implemented using an array. It ends up being semantics. But I say explain. Oh, actually, that's part of it. Anyways, are we good on that problem? Or do we want to talk about it a little more? Questions? And we'll move
So
on until I hear something.
storage efficiency is not always with symbol tables.
Yes, because if we remember back to the think of it like binary trees are one that if you were to just put all nodes in a binary tree into an array, how much space would it be compared to the binary tree? And at the end of the day, that it will be less. Although, doesn't he implement binary trees using an array? No.
Yeah, he does. So it wouldn't change anything, really.
Yeah. Okay. And then I guess the only situations is if you're talking about like hash maps, hash tables. At the end of the day, most symbol tables use some kind of array because you can use like indexing of some kind, and so it makes it easier in that regard. I guess think of it kind of like an array is a simpler abstraction of a symbol table. Therefore, it is more efficient than a symbol table because there's less complexities attached onto it. Does that kind of make sense?
Yeah, it does make sense.
It's the simplest form of data storage you can really get, besides having a linked base structure. And I have a train behind me. Hopefully you can't hear that. But
No, we can't.
any other questions? Dallin, Sandy, Halper? Anyone else?
I'm good to move on.
Yeah,
okay.
I'm good to move on.
Just want to make sure. Want to make sure we have majority here. Okay, next. Consider the following method discussed in lecture for deleting a node from a BST, binary search tree. What functionality is provided by the indicated line? This is the indicated line. First, let's understand what we're doing. in a binary search tree, we're first checking to see if we have a null node. Okay, we don't want to do anything. The second bit is we're saying, okay, how should I order these? If I were to compare the actual key of our node with the actual node I'm looking at, if it is less than, we essentially want to set the left equal to whatever we remove. And if it's greater than, we want to set the right to whatever we move on the right. Otherwise, essentially if they are the same key value, and we want to make sure that both the left and the right are not null, then we want to take the minimum on the right and then delete it from our tree and set the old node equal to the minimum. Okay, that's very confusing with that
Is it
actually
minimum or
visualizing.
the new node? 'Cause,
So
like he has node t equals x and then x equals minimum t dot right. So
my assumption was that somewhere it is, let's say you have some binary tree like this, right? And let's say we're looking at this node.
Okay.
I think the idea is to essentially say, hey, I want to take this, sever its connection, and I'm going to move it over here, and I'm going to shift everything over here down some, so that this now points to here. Where, or actually, oh, I see. So this now actually replaces the old node, I think. So let's call this minimum, and then desired node.
Isn't it just deleting the left? Wait, isn't it just getting the left root closest to the parent, rather than it being on the right?
The
Because on the right,
left
it's
root.
grabbing. Yeah, because like on the right, it's grabbing the most minimum on the right side, but on the x dot left is equal to t dot left.
Oh, I
Isn't it
see
just
what you're
grabbing
saying.
the close? Yeah.
Okay.
So it's
So
grabbing the most minimum on the right, and then it's just updating it whatever's on the left. Does that make sense?
yeah, I have to work through the problem to visually to really understand what you're saying really quick. So this is our x. This is our x node. We're going to take the right. We're going to set it equal to whatever's the minimum on the right. So we're going to essentially say, hey, point to here. And then we're going to set the left for, oh wait,
So the desired node is x. Is it x?
it starts off as x. So
Okay.
this starts off as x,
Mm-hmm.
and then x then becomes the minimum node. That happens
Wait.
right here.
But doesn't the minimum get deleted, or is that? Oh wait.
That hasn't occurred yet. So
Okay.
this becomes our x, but this is t.
Mm-hmm.
So we essentially say this is our t node, just as a reference.
Okay.
So we can refer to it back later. And we're saying, okay, we're now saying the right part of this node is going to be the minimum on here. Now, what I don't really understand is, wouldn't that be the... Oh, wait. Oh, it's recursive. This is confusing me. Where do you actually return the node? I'm assuming if the minimum has any connections. Wait, if that equals null. Okay. So we set the right of this equal to any nodes that are. So if there's a node like right here that our minimum was then attached to, we essentially want to set it over here, if that makes sense. Maybe. Yeah. Are you guys still following?
Fine.
Yeah.
Visually, this can be a little. Hold on. Let me actually look at the binary search tree visualization.
You're saying the x becomes the minimum?
Yeah, let's insert like a 5 and a 1 and a 2 and a 7. Give me some numbers.
13.
13,
4,
4.
6.
Okay. So the idea is if we wanted to delete 5, and I'm going to turn down this animation speed.
Can you zoom in or?
So we essentially want to find the largest node in the left, and we move the nodes we just copied. Okay. Does it not let you? Yeah. So we find the maximum on the left side, and then we copy the value to the old, like to the root, or where we found the yeah, we swap that with whatever node we're moving, right? And then we remove that node from the tree entirely. And then I believe, what if we're doing like?
Can you go back, reverse, like skip
Yeah.
go to the beginning. So can you delete 7 instead of 5?
Yeah. Wait, hold up. We had a 6, right?
Yeah.
Okay.
Okay. Delete 7.
So we find 7, and 7's been found. And then next we.
So it always, like when you delete, it always goes to the left.
We first have to take care of the left and right. So I think you deal with the left, and then you deal with the right. Maybe. I think the way he implemented it's the opposite. If that makes sense.
You went right, deleted the minimum, and then he updated it to the left.
Yes.
Can you guys hear me?
Yeah.
Yes.
Am I super quiet? Okay, I'm in a library, so I have to be quiet. Okay, I think I got the how this works. So the first, there's like an if and then else if and then else, and so these are if there's no children, if there's one child, if there's two children. And right now the else is the two children one, which is the hard one.
Yeah.
What it does is it picks the node that you want to delete, and it sets t and x are both pointing to that node right now. Then it sets x to be the minimum of the right subtree of that node. So it'll be like the leftmost bottom node of the right subtree.
Yeah.
And then that's going to be the new middle point. So that it is going to set the right of that new node to be to be the top of that subtree, except it deletes where itself would be, if that makes sense. So it's like you're moving that node to be at the top now, and then you're setting the left, that last line that we're trying to figure out what it means, we're setting the left to be the other half of the tree.
Yeah.
I feel like that didn't make much sense.
I think. Oh wait, because we have minimum on the right side, right? In this example, we have the minimums on
It
the
is.
right.
It's the minimum of the right subtree.
Yes, and
So it'll be on the left of the right subtree. That makes
so
sense.
if something was like here, is there a situation where this could happen? Where the minimum can point here? I don't
No, because
think so.
the minimum will always be at the bottom because you can't have something bigger than it underneath it
Yeah.
in a binary search tree.
Okay, so then I think I understand. I think it's saying like if hold on. If we had more stuff over here, we essentially want to reconnect it. It's essentially there to reconnect anything else we had on our tree. Since in removing this node, we then have to update the minimum on here so that it's now pointing to this tree. So
Yeah.
yeah, so it sets the old left subtree of X to be a child of the successor node being moved up. It's essentially shifting the rest of the tree so that it point. So now
Yes. Yeah.
it looks normal again. And this eventually like deletes itself. Sorry if that was so confusing. Are you guys still confused? Need more clarification? What's up?
Just to confirm,
Mm-hmm.
it deletes the minimum right side and it updates it to the left, right? What we're all agreeing on.
We were saying that delete starts at some node and then has to delete the minimum node on the larger side of the BST.
Yes.
And that ends up being the right. Yeah. And that's...
And
Oh, continue.
I know you were saying.
No, you continue.
Okay, and then it just updates to the left, right?
Yes. You're essentially replacing the node that you wanted to delete with the minimum node on the right side. And therefore, because you're doing that, you now need to update any old connections the other one had, aka anything that was on the left side of the tree that we didn't touch. I think I may or may not have resaid what you said, but are you still confused or are you more questions?
No, you're good. Just trying to confirm it.
Okay. Are we good on that one? No, BSTs are always confusing.
Yeah, I think I'm good.
Okay. Binary search trees are probably going to be the hardest concept in general. Hopefully. So yeah, the answer would just be C, because A, let's think of this as, let's eliminate the other answers just to make sure. Finds the in-order successor to X. This has nothing to do with finding.
Yeah.
Replaces the current subtree rooted at X with a new subtree without the minimal node. However, the current subtree rooted at X there's multiple subtrees.
Yeah, but I think like if we like look at the answers, we can eliminate A and D immediately because it does not update the size and it does not find. It replaces something or it sets something. So we're gonna have a 50-50 chance. So and then like from that we can figure out what is the answer.
Yeah, I just like
B is actually what happens to the right side. Like when you replace it, you're taking that subtree but without the minimum, because that's the one you're replacing it with.
Oh, so if the line was x dot right equals t dot right, we choose B.
Yeah,
Or-
if it was the one right above x dot right,
Oh,
it's like x dot right is equal to delete and t dot right. That would be B.
okay.
All right. Cool. Okay, ready to move on?
Yes.
Yeah.
All right, 3. Trace a non-balancing BST through the following operations. Tree.add. Okay.
Can you just do it in the visualization? I think it's easier
Yeah.
for us.
Well, this is a non-balancing. This is balancing, I think.
No, I
actually,
don't think
no.
it's balancing.
Yeah, it isn't.
Doesn't balance.
Whoever made this application, bro.
What?
He's goated, bro. The guy that made this application.
I think it was the university. That's an edu URL.
Oh.
Which still somebody at the university did, but
Yeah. So when we add the 3, first it's gonna compare to 6, and then it's gonna go to left because it's smaller, and then compares to 4, it's gonna go to left because it's smaller.
Okay. Let's test that theory. There you go. You're right. And then
For 7, it's the same thing, but instead of going 4 of the left, it's gonna no, I mean it's gonna go to the right because it's bigger than 6, and then it's gonna go to the left at 25, and then the left at 8.
Okay. Yeah, that seemed about right. And then 2.
For 2, it's the left first,
Then
and
left.
then left, and then left.
There we go. And then we're gonna remove.
For the removing, it's gonna check the left side. It's gonna first remove 6 and then go to the left, checks 4, and then yeah, I get lost here.
I think what it'll do is it'll start by traversing the right side and find the lowest number on the right side.
Mm-hmm.
And then replace that in the tree. I think.
Yeah, that's what was happening in the last problem.
Yeah.
It'll go to the right subtree of 6, pick the smallest one, and we'll swap that 6 and the 7, then delete the 6.
It's remove 600, not yes.
Oh yeah, I bet.
Yeah.
Oh, I ended up doing the left.
No.
I think ours does the
No,
right.
that's the other way you can do it. So it doesn't. You can either pick the smallest on the right side or the biggest on the left side.
Oh, so
This
you
one
have
pick the biggest on the left side. But in class, Acuna said just do the smallest on the right side, so that way it's consistent.
Yeah. Okay. That's the problem with Acuna's class. Like he's doing things and he wants us to do the things that he do in class.
Wait,
Like when
those-
you go.
what he wants is take the smallest on the right side, replace it as the root.
Yes.
Okay.
Yeah. Sorry, I accidentally closed out of it. Yeah. And
it
ideally,
works both ways though. Like, does it really matter like
Wait.
which way you go? If you can go like maximum on the left or like, the smallest on the right, can you just like do either or?
yeah. I mean, at the end of the day, I
don't-
think you can do
yeah.
either or, but his implementation of it, the one that we've been taught,
Oh yeah.
does the right
implementation of
side.
it. Yeah.
So, yeah, at the end of the day, it's an implementation detail, and you should probably look at how your program is actually implemented. But yeah. Okay. And I'm assuming you guys would know how to do the structure of it, and yeah, you just visualize it. You don't actually have to trace out like, oh, this dot, whatever.
Yeah. Just draw circles.
Okay.
Implementing a hash code function.
So consider implementing a hash code function for a string class. Which of the following statements is or are true? Select all that apply. So there could be multiple. Okay. So A is a hash function takes a string of arbitrary length and generates a fixed size hash. True or false? What do you guys think?
Hash function takes a string of.
I just want to ask you true or false for this specific one. We'll look at the other options, but because it's multiple choice, we have to go choice by choice.
I think it's true.
Yeah, I think it's true too.
Okay.
No, you're taking a like whatever the size of your string is, you have to fit it into the size of the hash table. So that's why we have overlaps, because we have to take something that could be potentially really long and fit it into like a fixed range.
Yeah. And if you want to think about this in practical sense, look at Java's hash code. Does the length ever change? No. Can you do it on strings? Yeah.
Oh, so like it takes any length and like it produces a length like SHA256 because like it has the same length, but it can take any values and like you need to have like 15 integers every single time. Even like if you input 20, a string of length 20 or length 15, you're gonna have 15 at the end.
Exactly. The idea is that no matter your input, it produces the same output, and that output is constant in size. Now, what that value is should change and should be determinate based on what your input is, but it'll always be the same size. Because imagine you're writing some database and you're storing hashes in your database, and your hashing function could give you a value from 100 to 5. There's going to be you're probably going to end up with a lot of hashes that are just not using the space they're given. It ends up being really inefficient. Whereas if you have the same size of hash, you can have an expectation. You can expect there always to be this size, and therefore this many number of combinations, unique combinations.
B is incorrect.
Okay, so
it's the opposite of A.
So a hash function that takes a string of fixed length and generates a hash of variable size. It's the opposite of A, therefore, no. We don't, this would definitely be wrong. Mainly because a variable size hash is not useful to us. And then C, a hash function may give different hash values for identical strings. True or false?
I think that's true.
Anybody else got a guess? What do you guys think? And what's your reasoning?
Okay. I'm gonna say that it's false, because the point of a hash function is if you put in the same string multiple times, you always get the same hash. So that way you can look up things and find the same spot in your hash map.
Yes.
So if you put in exactly the same string, you should get exactly the same output each time.
Yes. Mainly with with hashes, the entire point of a hash, the entire definition of a hash, relies on the fact that your output is tied to your input, and that your output is always the same if your input is always the same.
So that's why like we can reverse engineer the hash code to
yes.
to crack passwords.
Yes, the keyword there is not cracking. That's a I think it's called a rainbow hash. Essentially, if you were given every possible combination of a hash and you knew what input you put in to get that hash, and you just had a dictionary of all the inputs to their hash value, you could then figure out, okay, given this hash value, what's the password they used to make that hash? That's, I think, called rainbow cracking or rainbow hashing. That's the reason why they'll add things like called salt, where let's say two functions use the same hashing function, but every time you submit your password, they add a word onto the end or a number to the front.
So it does not look identical.
Yes, so they can't use the same rainbow hashing function on every single database. There's probably a lot better explanations for that and a lot better ways of doing that, but that is just an example.
Because like what I thought about hashing is that even though if you like put the same string, it's gonna give you different results every single time, so it becomes like more secure. But I think that's only applicable for some sort of hashing, not all.
If we were to do this, So these are technically different objects in memory. However, they gave us the same hash values when running this program. I don't know if you guys can see all this.
Yeah,
We can.
Yeah, and you can see that slight differences do have drastic outputs or drastic differences.
yeah.
Like you can see it at the surface level, it does seem similar, but as you can see, if I make this h a lowercase h, drastically different hash. If I make this O uppercase O, not that drastically different, but different hash. And I believe you can do 256. Yeah. I don't know. I haven't worked with that library enough to actually know how to do that, but I was going to show you like how you'd use those hashes to make consistent output, since SHA is one of those hashes that are pretty commonly used. Anyways, are we good on 4?
Yes. So only one right answer.
Yes.
Which is-
Only A. Since D is essentially saying
Yes.
all of them are wrong, which is false. Okay. Moving on to 5. Oh, did somebody say something?
Nope.
Okay. Just make sure. Is the hash code implementation in the following .2D class valid? What is, or that is, would a hash table be able to properly store keys with this hash code? Explain. So the idea is, if we have an integer x and y, and we return x modulus the integer max value, which
is 2 billion something.
Yeah.
2,173,000,000.
So
Wait.
What?
Isn't this pointless?
Why?
Modulusing with the biggest number. It's just all gonna give like.
You say it's the same value as x?
Yeah. Well, it's not gonna be the same value, but it's
No.
gonna be like they're all gonna be similar to what they were.
Yes. Like
So which won't change anything.
x, if x was 1 to 1 million, it's gonna give you the same exact number as x. That's what Alper meant. Because like x, like let's say x is 10. X modulus the maximum value is gonna be 10. Let's say x is 1,000. 1,000 modulus the maximum value is gonna be 1,000. So it's gonna return. It's just like you're returning x. So hash code is useless.
I would say you're right, except for I would be careful about using the word always, because that's not true always. What if you did integer.maxValue percent integer.maxValue? What would that return? If you have 10 modulus 10, what does that return?
I meant 0.
Exactly. Therefore, the largest value is equal to the lowest, or the not even like a middle value. It's not even the lowest value, which is not correct, and that would be a problem. So this, that's why I would stray away from always. But you are right; it does nothing to the value of x for majority of the cases. Now,
Or
there's another
let's say
issue here.
all the cases except or like almost all the cases.
Yeah, almost all the cases. Now, there's another issue here. Do you guys know what that issue is?
Negative?
No, that maybe. Aside from negative, there's another thing we're not addressing about the fact that it's a .2D, and that specifically we're only looking at x. What if we have 5, 10 and 5, 11? Those are two distinct points. Therefore, our hash table should treat them as two distinct points. However, this hash code would treat them the same. It would think, oh, give me the hash code of these 2 points. Okay, so it's just 10 and 10, because that's their x value. The hash code is just equal to whatever their x is. So that means no matter what their y is,
You're gonna turn the x to the y value.
Yeah, which means this is essentially saying, okay, We only care about this number when hashing. Therefore, we don't care about y, and it doesn't matter when we're trying to hash them. Even though that's not true. We know that points that line up on the x-axis are distinct. They are not the same thing. And for that reason, we know that this is not the proper way. I mean, we've explained that it's not the proper way, but let's see what some of the possible answers are. So yes, it implements the required hash code method using the attributes in the class. That's false. We just explained how it doesn't use every attribute. The second one, yes, since max value is larger than any number, the modulus doesn't change the value of the point, and no information is lost. That is technically false, because max value, modulus max value, will change the value of the point. Therefore, this is false in more than one way. C, no, the different point 2Ds might have the same hash code. This statement is correct. Different point 2Ds might have the same hash code, as we mentioned. Y doesn't get taken into account. And then D, no, it is missing the modulus by M. Well, that doesn't really make too much sense. Yeah. I mean, it has a modulus, but hash code isn't supposed to do modulus. If we think back to how we implemented our hash tables, the only time we did modulus was trying to fit it into our array. When we actually took the modulus of a value, it was after we already got its hash code. So given a string or a box or a dog, we only cared about their hash code. Therefore, we never did any modulus with that. If that makes sense. Oh, I don't know if I explained that properly. The idea being that this is not the data structure. The data structure should handle modulus. We don't handle the modulus of some m because we are not a data structure. We're not fitting it to some size, which m represents some size. Does that make a little more sense? Maybe. I lost you guys. You're completely lost, confused.
No, I like understand it. I get it.
Can you clarify that a bit one more time? Like, what do you mean by that?
Okay. On the m bit?
Yeah.
So, if you have some data structure, right? And you split it up into parts, right? You know how many spots you have available, right? 1, 2, 3, 4, 5, 6. That makes sense. So if you have some unique ID of every object, and you take the modulus of m, aka m is our 6, this is how many spaces we have open, then we can figure out, okay, it should go here, right? Or it should go here. That makes sense. But what if you are the thing being stored in there? What if you don't know of the data structure itself? You are just a point. You have an X and a Y. You don't know of that hash table's existence. Therefore, how are you supposed to know what M is in the first place? You don't. You don't know what M is. I mean, you can't. There's no possible way for you to know what M is. And that's why we can't just say, oh, we have to modulus by M. It just makes no sense. This only exists here. There's no M. Whereas with a data structure, we know how many things we're trying to store. Therefore, we know what we need to wrap a number by. Because when you modulus something, you can think of it kind of like a wrapper. If you have a bunch of wrapping paper and you're trying to wrap it around a box, you have to Like the wrapping paper doesn't know the size of your box. So you have to make sure you put that wrapping paper all the way around it until you no longer need the wrapping paper, and then you cut it. That's kind of what like modulus or remainder or modulus m is doing. You're wrapping the value by saying, okay, not here, not here, not here, not here, and here. Okay, let's wrap it back around. Keep going, and you wrap back around until you find your spot. If that kind of makes sense. I don't know if that made anything more clear, less clear, confused.
I got it.
Okay. So you good on that? Do you have any more questions?
I'm good.
Okay.
I'm good.
Awesome. Now 6. Imagine. Oh wait, just to clarify, we have C was our answer.
Yes.
For 6, imagine that you have a linear probe hash table with modulus equaling at 11. Draw the final hash table after adding these keys: 34, 13, 10, 3, 0, 15, 14. Use the hash function hash k of I, k mod 11 plus I. And then doing modulus 11 that, where I is the number of times the algorithm has tried to insert the key. Your drawing should include the main size M array. Okay. So, if at any point you don't agree with something I'm drawing, speak up so I know to stop and explain. So we start off with this array, and we're going to make it break it down to like 11 parts. So that's half. And then I'm just going to draw it out. So 4. I think that's 11. 1, 2, 3, 4, 5.
The
6,
exam
7,
on Wednesday, is it going to be
10,
at
11.
12 or was it 11:45?
Give me a sec.
I don't remember what time you said, but I just remember it was Wednesday. I think I feel like it's usually around class time.
9:50 to 11:40, I believe.
Oh, it starts at 9:50?
Yeah. It's because they're set on final schedule, which is not class schedule. Class schedule is at 9 to 10, or it's from 10:30 to 11 because of the finals. Like every class that has a normal time from, any class that meets on Monday, Wednesday from 10:30 to 11:45 will have their exam from 9:50 to 11:40. If that makes sense.
Oh. Damn, I actually gotta wake up earlier then. Okay.
Yeah, to not miss.
Sure. I work all in the morning, so I'm already here.
Gotta set my calendar real quick.
So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Draw in one more. Actually, Sorry about this. Okay. So first off, where do we think we should start? So we have the number, we need to insert the numbers. $34, $13, $10, $3, $0, $15, $14, right? And for sake of ease of use, 34 mod 11 will be 1. 13 modulus 11 is 2. 10 modulus 11 equals 10. 3 mod 11 is... Wait, is that right?
Yeah.
Alright. Just going to keep this as a reference on the side. Okay. So, where should we first put the number 34?
In 1.
Give me a second, I need to reach the size of this. You say in 1, okay. So that's where 34 goes. Then next we have 13. 13 is going to go where?
2. Well, it's gonna disappear.
Sorry about that. It's just using MS Paint, which is not the best.
Oh yeah. I don't know why you are, but I guess it's simple. So
It's simple. It does what I need it to. 10 is going to go where?
to 10.
Okay. Which path is open? Let's turn this into Dora. Can you see where 3 can go? Probably where 3 is.
I know.
Great.
I swear I still don't understand. In class, he was like, yeah, so when doing linear probing and stuff, you're only gonna go like 2 or 3 apart on average from where you belong. Or was that the other method? What are the 2 implementations? Linear probing and
linear chaining or hash or table chaining, something like that.
Chaining, yeah.
So I think the reason why he said that is because the implementation that you use will typically say, hey, keeps at least 70% capacity, or I think 75% capacity. Like, if you ever go past this threshold, increase the size of the array. Because we're getting too full, it's going to take too long to do these operations. We need to make sure that we're fast and snippy. And whenever you what?
So that means when you're increasing the size of the array, that means you have to rehash it, right? In some ways.
Yes, it does. However, we're essentially kind of, let's say you have, I don't know, you're running a school district, and you only add students maybe, well, yeah, unlikely, but let's say you're hired to redo some.
Yeah. I was just...
I know. The idea is you're gonna have such a large sample size that once you get to 70% capacity, you're gonna know, and that you can maybe take, like, I don't know, over the break, you just make a copy of some database, and you just maybe double the size, and you rehash everything into it, and then you swap them when you can. That's the more practical or realistic situation. However, in what our implementation is doing is just so we add something. The worst case scenario is we have to rehash and double the size. But I think the way he wants us to see it is just that. Let me see if here's module 10. Let me see if he puts the actual big O notation in the bottom. For chaining, n over 2m is the average search hit. So the number of elements we've added in over twice the modulus size. So in this case, it would be what? 1, 2, 3, 4, 5, 6, 7. 7 over 22. 7 over 22. And how much did you say? At most, you check like 3 times.
He said 3, I believe. 2 or 3. I don't remember.
There's a 3 here. This is pretty close to 11. Actually, here. 0.33 times 11. Yeah, about 3.5 is how much you'd have to search. The average search hit of this hash table. It's just, I think, how the math checks out. I don't think there's some special nuance about how it operates that does it. It's the idea that as long as you make sure that you contain a certain capacity, or empty capacity, and then increase the size as needed, you shouldn't end up doing more than this on average. Just like how you may have an average case for the different sorting algorithms. For like insertion sort. On average, you have, it's escaping me right now, but on average you have some performance. There is still worst case. Worst case for linear probing might be that you have to traverse 70% of the array, if not the entire array. However, the goal is to avoid that situation by doubling the size, so you don't run into the worst case. Does that kind of make sense?
Yeah.
So what did we say that the runtime was for this, like the hash functions?
The hash functions are constant. We assume constant because any arithmetic operation is considered constant.
So 1? Or was it 01?
Yeah.
01.
O of 1, when I say constant, it just means it could be 1, 10, 20, or whatever, but when you're using big O, you essentially don't care about the magnitude, you just say it's 1. It could be 20, but we consider that 1 as big O, which is where you may have some problems, because if you have like I knew this was a tricky question. If you have like 4 int I equals 0, I is less than this. If I were to ask you, hey, what's the big O of this function? This is O of 1. Like, it may feel wrong to label that as O of 1, but that is terminology-wise correct. Because no matter the sample size I have, it'll run the same number of times. It's a constant number of times. It does not change. However, it's a horrible way of implementing, and we should probably shoot the person who actually implemented it, but that's a different problem, different discussion entirely. I mean, you probably shouldn't loop over something a million times constantly. You should probably redesign and have some a bit better design choices if you're doing this. But in terms of specifically defining big O, this is big O of 1. The growth function, however, that is where things change. This would be more of like, the function would literally be like 1,000,000 plus, or whatever this number is. This would be like 1,000,000 plus however many other statements we're measuring. So it'd be 1,000,000 here. And then you'd have like 4 here. Therefore, growth function is f of n equals 1,000,004. This would be like the growth function of it, essentially. It kind of makes sense. I know this is a little side tangent, so apologize,
Yeah,
but I noticed on a couple of the exams he likes to throw in that kind of thing as like a trick question when you're trying to determine big O. You got to be careful of that. Back to the actual.
Yeah, we were doing the question.
Sorry, I get on side tangents. Next one we put 0 at 0, and then here you put 4 at 4, or 15 at 4. And then here is where we have our first collision, is right when we're trying to do the last one. So this hash ends up being 3, which should be right here. But we have a problem. There's already a number there. So what do we do next? If we know that 14 is supposed to go here, but there's something already there, what is the first thing we do? And
Make a linked list and add it to it.
no, because that's a different type of hash table. Keep in mind we're doing a linear probe hash table and not a chaining hash table.
I got confused because you made it vertical.
My bad. I do that just as a mentally.
Because in class we did the array thing, like just, you know, in the X.
There you go.
Yeah, well, it's alright. I get it now. I just confused myself. That's why I said it was, because that's how we did the chaining.
Mm-hmm.
My bad. Yeah, my bad.
No worries. That's just at the end of the game. At the end of the day, just a visual misconception. It's fine. There's no like conceptual issue there. But
okay, but I do know what we're gonna do.
Okay.
We check the next available space.
Okay, so we check here. And what's the result?
Again, it's already taken.
Okay.
So keep on repeating until we find a place.
Okay. So here.
Yeah, so the I incrementer is far right for the collisions.
Correct. That is our I in our hash function. Our hash ki. K is the actual key. K stands for key. Our key is our 34, 13, whatever that. And then you mod that, so you get like 14 mod 11 is 3. And that handles that. And then plus I. I is the number of collisions. So in this case, we had 2 collisions. So our first off, we did 0 collisions here. Then there was 1 collision, so we went to here. And then we had another collision, so we went here. So we end up having an I equals 2, and the hash of 14 comma 2 equals 5. And therefore we're going to put our 14 here. Now, do you know why this is here? This is also here. Do you know why? Can you think of an issue where the output of this causes a problem? Anyone?
I'm really not sure.
It's so it wraps around if your eye gets too high.
Yes.
Like if you try to put something in that 10 spot but it's already filled, it'll wrap around back to the 0 because of the extra modulus.
Exactly. So if we had 21, for example, if we tried to take 21 modulus 11, we'd get here. And plus 1 would be 11. And if we tried to index at 11, we have an array index out of bounds because 11 doesn't exist. Therefore, we need to model 11 again so that it wraps back around to 0. Does that kind of make sense? Maybe, sorta.
Yeah, it makes sense. Because not every time. We're gonna be looking through the whole array. We could be starting from like towards the end of the array and not have a look through half the beginning where there's available spaces.
Yeah, because it may be dangerous to just add the number of collisions on without actually considering that we're using this for an index and that index has to be valid. So, yeah. And in a chaining, I should say, in a chaining hash function, we only need this bit, this k mod 11. The rest of it doesn't matter, because collisions wise, doesn't matter. I think we had to do in the two chaining, the double chaining probe or something. What is it? Something where we had a double chained hash table. Like you had two spots you could go, and you had to pick whichever one was smallest. That's one of those cases where you'd essentially have this again, where you'd wrap the value around just to make sure you're not getting a linked list that isn't actually in the bounds of the array. Sorry, I keep switching tabs. Are we good on 6? Or do you want me to draw anything more?
I think I'm good.
Okay. Everyone else good? Dallin?
I think Alan's correct at this.
Yeah, I'm good.
Okay.
But for the chaining, there won't be any I, then they'll just be calling it as regularly.
Yeah. Exactly. I believe if we look at the two probe chaining, specifically, yeah. Well, this one's formatted a little bit differently, but the idea being that you just have two different hash functions. But yeah, there's not that much. Yeah, it's basically the same thing. You just choose which one to use. Sorry, did that answer your question? I feel like I either did answer your question or I answered a different question.
Either way, you answered the question.
Yes. I just don't know if it's the right question. Triple?
Yeah, I'm good.
Okay. I just want to make sure. Okay. 7. Consider using the DFS algorithm, depth first search. From a performance standpoint, would it be better for the algorithm to use a graph ADT, implemented using an adjacency matrix, or an adjacency list? Explain. So if we're looking at, first let's talk about which algorithm we're using. Depth first search. This one means that we're going to recursively kind of like spread out as fast as possible from some node to traverse the actual graph.
So we're gonna keep taking the paths down each children without looking at every, like, basically go forward deep rather than go around first, or
Yeah.
like around your vicinity, right?
Yeah, it's kind of like if you're going on a hiking path and the first path you saw, you went down it, and as soon as you hit a dead end, you went back, and if there's any other path, you go down that one next. And you keep repeating that process until you eventually end up back at your car, where there's no more hiking paths. I don't know if that made any sense, but
Or
kind of like,
or you run out of water.
yeah, essentially. If you end up getting eaten by a crocodile kind of thing, like if this is your
In
parking
Arizona?
lot. Yeah. Yeah. Never seen an alligator in Arizona? No.
No, I have not.
Fair, I haven't either. But tell me
Okay,
if you
good.
see one.
I'm not in Florida, mate.
Exactly. The idea is like, okay, go to here. Oh, the first path. Oh, it's a dead end. Okay, so I'm gonna go back now. Oh, this path. Oh, there's a new path. Oh, I'm at a dead end, so I'm gonna go here. Oh, there's this path. Oh, I'm at a dead end, so I'm gonna go back down here. Oh, this is the path I haven't gone. It's a dead end. And I'm back in my parking lot. It's kind of like that. Although you probably can't see. That looks so horrible.
That looks
Sorry.
terrible.
I apologize, but it's a
Not
video.
accepted.
It's a video, you can play it back. But
I mean, we should probably use a graph because we learned to use it with a graph. Come on.
well, it's a graph in the first place. Both of these are graphs. A matrix and a list are both can be represented, or you can use a graph to represent them. That's, I think, maybe where You don't want to confuse them because a matrix is a data structure. A list is a data
Oh.
structure. An adjacency matrix describes, okay, this data structure represents something. I'm using it to represent something. Like a list, like a list of people who finish first at the Olympics or something. That the data structure is a list, but it is representing the people who finish first or something. So you want to separate the actual data structure with what it's what you're representing with it. And in this case, an adjacency matrix just means like we have some matrix, so you have something like this. You have grid, essentially, grid-like structure. And here you're going to have your from nodes, call it, or, yeah, from. And here you have your to. And when you store here, is you essentially say, okay, is there a way to get from this node to this node? If there is, you take it from here to here, and you say, this is true. And is there a way to get from this node to this node? Then you put a true there. Otherwise, you just put false for everything else, essentially. And what this actually represents, or what the data structure is, this is just a 2D array of true-false values. However, what it represents is saying the row is our from, or our source vertex / node or whatever. Our column is our to. This is our destination, our to node, and the value stored at that row and column is a true false, whether or not there is an edge from the source node to the destination node.
And how do you do self? I forgot how to do self. How do you show that you can go from yourself to yourself? Like there's an edge from
cannot.
yourself.
Well, actually, no, man, you can. So, let's say all of our nodes are labeled by a number. 0, 1, 2, 3, 4. And then on the side, 0, 1, 2, 3, 4. If you wanted to say that there is a way to get from 0 to 0, you just put this true. Anything in this diagonal is a self node.
Okay, so you didn't make a self node initially.
Yeah.
To what you put.
Maybe
Okay.
as an accident, but you can represent both a directed and non-directed graph using this structure. However, the limitations are that you can only describe one edge, and you can't apply. Well, yeah, you can only apply one edge, if that makes sense. But the
What do you
benefit.
mean
So
by 1 inch?
if
Doesn't
you,
it just make it symmetric if it's?
what
So
if
you basically use like half of it if you're a directed graph.
that's yes, that's for if you want to save space and you have a non-directed graph, meaning like the from and to both connect to each other, you can just get rid of this half of stuff. You can get rid of this side because you can represent the same thing with only this information. What I was referring to is because it's a 2D array of true false, what if there's two ways to get from Arizona to California? You can drive or you can fly. Or you can take the bus. You can ride your bike. There's more than one way to get from A to B. Therefore, but if you just say, yes, there is a way to get from A to B, you do not have the ability to, you're not describing that there is more than one way.
Well, wouldn't you know that by looking at the specific column or the row?
If you stored some kind of list of edges, yes. However, if you say true, false, given a row and a column, you can only ever know, yes, there is an edge, no, there is not an edge. That's the only information you're storing in a 2D array of booleans. However, if you had something that was like, so for reference, this is our basic adjacency matrix. And then if we wanted to store a list of edges, what we can do, which is not really recommended because it's space costly, you'd have a linked list array, a double array, and then you can just store every edge. So it's a linked list of edges stored in a 2D array. However, we don't do this as it's very space inefficient. Like, if half of these nodes don't have a value, you're just wasting space. So instead, what we do is we have a adjacency list. An adjacency list is just a linked list of edges and an array of those. Does that kind of make sense?
And okay, an array of those, but how do you? So like, would it just tell? So if it's true, you put it in the array, basically.
It's kind of like, if we had a, you can, so if you have a, you can fly to Cali, you can, oh, come on. You can bike to it, or you can drive to California. And does this kind of make sense?
Oh, okay.
In the same way that you can fly to, or you can drive. I'm going to abbreviate it. But let's say there's, I don't know, the airlines aren't actually letting you do return flights. Then we could essentially just not add that you can fly to Arizona. This can be used to represent a graph. You can visualize this data structure. And the trade-offs here is that in a matrix like this, it's very, because you've already defined the space that you're going to use, you've defined how many source nodes, how many destination nodes you have. It's very quickly to find some number of edges given those two things. However, because you've allocated so much space, it's not super memory friendly. We may be using redundant amounts of data, and it may be costly if we're doing something that we want to preserve memory or data or space. I meant we might not like this approach. However, with this, we only have to allocate a single array for the actual list of vertexes. So if we have 10 vertexes, we only have to make a list of 10 vertexes and a list for every edge that we make. And for a adjacency matrix, we have to allocate the square of how many vertexes we have. So, I mean, as you can expect, it's a square. So if you have 10 vertexes, you have to allocate 100 spaces in your adjacency matrix. Whereas our adjacency list only has to allocate 10
Plus however many
spots.
edges.
Exactly. And also in this situation, if you're not doing booleans and you're using a linked list, you then also have to add on the edges that you have. So you end up adding more complexity to your data. If that makes sense.
Hmm.
Okay. With that out of the way, also actually, anybody have questions on that? Triple, Alan?
We good.
Okay. So consider using the DFS algorithm for performance standpoint. Would it be better to use an adjacency matrix or an adjacency list? So let's look at the options. An adjacency matrix, it will provide faster support for visiting each of the adjacent nodes. Visiting the adjacent nodes that's technically not true. Because if you think of it, if I want to know what's adjacent to 1, I have to look at all of the values here. I don't necessarily know which ones are true and which ones are false. I would have to go and check each and individual one. And that's assuming we're using directed. And undirected, we may also have to check for this row as well. Because something could be pointing to us, but we're not pointing to them. Or vice versa. Well, yeah, anyways. We'd have to check every possible connection. So we're essentially checking every vertex that we have on our graph. We're checking it's like checking every state just to see which states are neighboring California or Arizona. Like, you only need to look at the things nearby rather than looking at every state in the US. Does that make sense? I feel like that was a bad analogy.
I know, but it makes sense.
Okay. B, it will provide faster support for checking if 2 nodes are connected. That is true. Because you're using an array lookup, which is going to be O of 1, it's very fast. Then, given you know both the from and the to, or vice versa, you can determine if they're connected in any way, or directly connected in any way. If there's some node that points to that node, which points to that one, that's different. But if you want to know if 0 and 4 had some connection, all you'd have to check are these 2 boxes. And if neither of those are true, then we know they're not connected, or directly connected, I should say. And this may be semantic slightly, because I don't know if he considers connected as like something that is node to node to node. Like, is A connected to B? Or is A connected to C?
You're saying he would have called it an adjacent node?
Maybe. I don't know if that's just semantics, though. It's possible. I'm just saying I would be critical of this word. connected, as I could argue that A is connected to C. It's just it looks more like A and C are A and C are whatever he does, the squiggly line. Like they're connected to each other some way. There's a path from A to C, if that makes sense. And yeah, I think saying that checking if two nodes are adjacent would have been a little better.
If what we're assuming is what he's assuming.
Yeah.
Yeah, yeah, okay. Maybe other answers will be more obvious than that one.
Yeah. Like I said, I'm just going down the answers just to mark off anything that may or may not be ambiguous or obviously wrong. So for C, an adjacency list, it will provide faster support for visiting each of the adjacent nodes. Arguably, yes, because the best case is that they are equal time. Oh no, the worst case is that they are equal time. If every value in here is true, then it'll take the same amount of time for a list to go through every node in it versus a matrix. But the worst case is that let's say only the last, let's say 1 and 4.
You mean the best case?
The worst case of the matrix. The worst case for the matrix is when there's only one connection and it's the farthest away from where they start searching.
Yeah, but worst for the matrix, yeah.
And therefore, I would say...
Which would be the best case for list?
Yes.
Okay.
And then adjacency list, it will provide faster support for checking if two nodes are connected. No, because let's say there's a bunch of nodes in between here. Let's say there's like 100 ways to get from Arizona to California. And let's say at the very end of this linked list is driving to California. If I want to check, hey, can I drive from Arizona to California? I'm going to have to go through every single one of those items to check that. I can't just quickly be like, okay, is California in this list? I guess a better explanation is, let's say you can drive from Arizona to Florida. To Florida, to Minnesota, to Alaska, Canada, Mexico, whatever. You can drive to all these other states and you want to check, okay, can I drive to this state? In a linked list-based structure, the worst case is checking every possible element in that list, which is not what we want. Instead, what we should be doing, well, it's just not, it's not that we don't want that.
Not possible, really.
Yeah, it's just not possible in the linked list, sorry. I'm so used to like saying arrays are better. Arguably, I would do, instead of a linked list of edges, I would do a hash map of linked lists, but even then that's still not going to help us here.
So we're screwed because both B and C are correct.
Not B. I said arguably this could be wrong.
Yeah, but it's okay. I just thought about it, but like then if that's what it means, then why then did we talk about like D as if they were just in a way connected?
Oh, D is wrong.
Okay, I guess what I'm trying to say is, doesn't A already cover the adjacent part of the problem? Like checking. Okay, we're checking the speed of the
So.
Okay, A and B would be repetitive if B is what we think it means, rather than just are the two nodes connected.
think it's C because I don't think with the DFS you don't really need to check if it's connected or not. You just gotta check if it visits, right? Yeah.
Wait. It'll try passport.
Oh, I totally forgot about DFS
Yeah.
itself.
Yeah.
Yeah, in the
So like
context
DFS
of,
and stuff, we're just like visiting each of the points. So I don't think it really matters if it's connected.
we don't in DFS we are not checking if A and B are connected. Rather, we are traversing it based on the connections that some node has. Based on given A, what are its connections? I mean, that's true for like both algorithms, I believe. I believe, well, yeah, right? I think so. No. Because DFS, or no, BFS has to check whether or not two nodes, or a node has already been visited, right?
Well,
Oh, then
isn't
you
it same
mark.
for DFS?
Yeah, I think that it doesn't really matter. This doesn't matter in the context of searching. So I think that's the assumption we'll go off of. This doesn't help us in our problem, specifically DFS or BFS. But because we need to visit each of or we need to visit every adjacent node, we want
Yeah.
that to be quick. And I believe we also want we just want that to be quick. Because in a matrix, both of them would be the same, I think. No. The BFS would end up searching more? Yeah, because it would be searching the empty tiles. Yeah, anyways. Regardless, C. Questions? Clarifications? Anything? I'll still form a questions, comments, concerns, complaints, critiques.
No, bro.
Nah, we get dog.
Okay. I think I have used that phrase outside of class, and ironically, I think it's starting to stick.
No.
He doesn't wait long enough after those, though. Or at least, I don't know, people feel intimidated to ask questions.
I feel like I asked a lot of stupid questions.
Stupid questions are okay. At the end of the day, it's better to ask a stupid question than nothing. Because it's more stupid to stay silent than it is to ask something that may be obvious. Because if it's something obvious, you can answer it with like a snap of your finger. Like it's a very quick response. Or if it's obvious as in it's like you should know something different, it's better to get that clarification then because you'll be able to understand things later and it may actually help with the next thing you're learning. That's my methodology upon it.
Theory.
Yeah.
In which of the following scenarios would you select using DFS algorithm over BFS?
Stuff that would apply. So there's multiple here potentially. So A, you have limited memory available for storing immediate results, and you are given a wide graph.
If you have a wide graph, you use BFS, correct?
A wide graph is
We had the quiz on this quiz
Mhm.
question. Or was it
Yes.
a short answer?
Yeah, no, yeah, we did. I think a wide graph is referring to
Like on the X, yeah.
the idea is that their connections are spread out.
But they're shallow, like from
Mhm.
the top node.
The idea that no node really has a bunch of children that it has to go to. Like there's nothing like this.
Wide just means not deep,
Yes.
basically.
The problem with that is that like I think he's basing it off of visualization. That you visualize something with a lot of children as something very like tall and versus something that is wide is something that doesn't have many connections and is kind of like it's kind of like a social media network where anybody has only 1 to 2 friends. Where a wide graph is kind of like where somebody has 1,000 followers or 1,000 people they're following. If that makes sense. Like, if you are doing if you're doing BFS, you are assuming there's only a handful of things you need to visit given a certain situation. So like you only have a handful of neighbors. It's probably best to get to know your neighbors first, and then you get to know their neighbors first, and then you keep on repeating that process. Whereas with DFS, it's better to like, okay, I'm gonna get to know my neighbors first, then their neighbor, then their neighbor, then their neighbor, and I keep doing that until I find the grandmother's dog's cousin's fish,
Nice.
which is like memory wise, all you have to remember is like what people's houses have you visited trying to search outwards. But um, with a wide graph, you essentially are like, okay, given a social media person with 1,000 people following them, then I'm going to look at each one of those followers and see how many followers they have. So imagine you have somebody who's got like who's followed by a bunch of other famous social media people. You're very quickly going to grow the amount of people you have to search. It very much your scale starts to get very large in memory wise. So, and we're trying to say when you should use BFS or DFS, which is over BFS. So, yeah, A is true when you're given a wide graph, aka you want to search for.
So this is what he meant by wide and deep. I put in. It's from the short answer.
Oh, I just put the same picture in no mic.
Oh.
Now there's 2 of them.
Oh.
Awesome.
Yeah, this is confusing for me too.
Basically, when there's a lot of nodes, is what it meant by wide and deep, or
when there's a lot of connections.
Okay, I think deep just means from the starting node to the end node, like the deepest you can go, basically. What's that length? And then for wide, that's not very long. So you can only go you can only hop like 2 children, and then you get to the bottom. But one on the right, you have to go through 3, 4, 5, 7. That's like 3 children at least to get to the bottom of the.
Mm-hmm. You start off with this, and then you attach these 3 with BFS, and then you end up attaching these. And every time you attach more, you kind of erase the predecessors. So it's kind of like you now have 4 that you're searching. Before you had 3 that you were searching. Before that you had 1. In this situation, on the right, you start off with 1, and then you start searching 2, and then you start searching 1.
For wide, you said you should use BFS, correct?
For a wide graph, you should be using BFS, yes.
Yeah, so it's supposed to be the opposite, actually. That's what it was in the short answer.
Where you should be using DFS on this, right? Depth first.
DFS on the left one.
Yeah.
BFS on the right one.
Yes. Because the idea is that you go here, here.
I mean, the idea of DFS and BFS, and then your choice of using those in terms of wide and deep graphs didn't make sense because DFS is is a way of going deep in first, right?
Mm-hmm.
And then BFS is staying like close proximity to where you started before
Mhm.
you go deeper. But then they're like the opposite once you have to actually use them.
Mm-hmm. The way I like to understand it is that BFS requires a lot of memory when you're building things like a pyramid scheme. So have you ever seen like a visual of a pyramid scheme? Like pyramid
Yeah, I watched
scheme.
The Office.
Scam companies.
Yeah, the scam companies are like, okay, if you're near the top, you must make the most money, and then like this kind of stuff. Like then you just have to hire people below you, and then those people hire people below you, and you can see very much how large this scales up, which is why like eventually it kind of, if you're near the bottom, you don't make any money. If you're the person who created it or the people who helped create it, and you make this very deep, yes, you make a lot of money, but it's again scam stuff. I'm not really talking about that. The idea is that if you were to search this with BFS, you start at the top, then you essentially go by layers. So the second layer, you're only looking at 2 people. The third layer, you're looking at 4 people. The fifth layer, you're looking at 8 people. And you keep getting larger and larger and larger. And that's very memory inefficient. Whereas if you were to search with DFS, the idea is, okay, start from the first, then the second person right here, then the third, then this dude, okay, then this dude, okay, not him, okay, here. Does that kind of make sense where you're kind of...
It all has to do with memory. Like once
Mhm.
you start trying to understand
So
why.
memory wise, BFS wouldn't be good. Oh, you're sorry.
No worries. Like you start here, and with DFS you go to here, then you go to here, and then you kind of erase a little bit, and instead of going right here, I should do this. You essentially say, okay, this dude doesn't have any people under him. I'm gonna erase that, and I'm gonna go to the next person. Okay, he doesn't have anybody under him, so I'm gonna erase that. He's no more children. Okay, I'm erasing that. And you can see this line never actually gets too long.
Yeah.
It ends up keeping pretty short. Whereas with BFS, breadth first, you're essentially saying, okay, start here and here, and then go here, 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 and here. And then you're going to erase this line. And then now you're going to go here, here. Like you see how many lines are happening every time you go one more layer deep. Like this is now much longer
Is that
than the
actually
one you
how
had.
it works though? I thought like you only focus on like one pair of children. Can you? This wouldn't actually how you. Is this how you actually would trace it?
Yes.
I thought you would only go like you would pick a children, you would pick a child, and then you would go to the childs of that, and you would go to the childs of that. Not like you would go to all the children and then all the children of the children.
This is how you do it. You go to the children, and then all the children of that children, then all the children of that children. That's, if you think of it like every step, you have essentially one phase, which is add who you're currently, you add the root, and then you're saying, okay, while this list isn't empty, I'm going to add all the children of the people in this list. So for the root, that'll only be 2 people when we're starting out. And then we're saying, okay, now our list is full of 2 people. We're going to empty that list or that stack of, and every time we look at another person, we're going to add more people to that stack. And then these guys get put onto the stack. And then as we're going through it, we're kind of removing things. Like at every point, you assume where I'm drawing circles here, assume that's those are people stored in the stack. And this is me running as the compiler. I'm looking at people, and once I'm done looking at their adjacency, I remove them from the stack. And you can see how I start building out a layer of all the children that were below me.
Okay, yeah.
That makes sense. So, and then eventually I'm like, okay, back to this dude. He doesn't have any children. Till eventually, I'm done.
But at one point we had too much memory.
Yeah.
Where it was like 8 people in the stack.
Yeah, you can kind of think of it like eventually you're gonna have majority of the users on a social media platform. If you're just trying to find, okay, how many people are connected to this person or whatever. And the better way of looking at it is like, if you ever looked at like Steam and you follow your Steam friends, you go to your Steam friend, you go to their friend, and then you go to that friend's friends. You're essentially doing a DFS. You're doing a depth first search. You're going from friend to friend to friend to friend, rather than if you were to go to your friends list and then open a new tab for every single person on their friends list. And then you go to each of those tabs and you're going to add a new tab for each one of those people on those friends list. You very quickly start having a Google Chrome full of tabs, right?
And then you're screwed.
Yeah, too much memory. Chrome will eat your computer. But
This is a perfect segue for our sponsor today.
Opera GX.
Opera GX.
No, but yeah.
Basically, you want to hit a dead end as fast as possible. Because once you hit a dead end, you can go down where you've been keeping tabs of other places to go.
Exactly. You can press the back button. And Chrome only remembers the places you've been. It doesn't, and well, yeah. Let's think about. Let's imagine Chrome doesn't have a forward button. They just have a back button. They only have to remember where places we've been, whereas in our other analogy, we had to make a new tab for every single place, which is bad. Anyways, so on about A, you have a limited memory available for storing intermediate results, and you are given a wide graph, which was shown here, a wide graph on the right. Should we use DFS or should we use BFS?
No, wide is the left one.
Is it? Is
Yeah,
this wide?
yeah. Yes.
Oh yeah, it says left. Okay.
Okay.
We have a wide graph.
If we have wide, we want to use BFS. Fuck.
Wait.
DFS.
DFS, yeah.
Sorry. Excuse my language.
No worries. Yes.
All that explaining, and Hunter's like, God fucking damn it, this guy's retarded.
No, you're good. I paused there, not as like a, are you kidding me kind of thing.
Yeah,
it's
you're
more of
checking
like a,
it yourself. Yeah.
yeah. My brain's, I go into like processing mode. I got a slow processor in my brain. I'm still running an i7. Nah, more like an i3. We'll get there eventually though.
Okay, yes.
Yeah. So essentially, we want to use DFS. Therefore, this is true. 2. You need to find the optimal solution that is the shortest path for the given problem. You essentially want
But
to
this
look.
was such a general.
It sounds like dexterous.
Yeah, it is dexterous. Dexterous was about finding the shortest path. And if we look at the description of dexterous, which I should probably explain because I know there are some people who weren't there last class. Dijkstra's is kind of like if you were to traverse a list and say, okay, starting from 0, what is the distance to get from or get to this node? So from 0 to 1, it's 1. And this is a better example. If I wanted to get from 0 to 2, it's going to be 5. If I want to get from 0 to 3, the best case is going to be a 3. if I want to get to 0 to 4, the best case is going to be 5. That's essentially what the algorithm's purpose is. We're essentially relabeling the weights. So like, okay, getting from 0 to 4, it costs 5. That's essentially what our algorithm's doing. And so we can measure the shortest path from this value to any node on the graph. The implementation-wise is we are essentially doing a DFS, a depth first search, on the smallest edges, or the least costly edges. And every time we arrive at a node, we sum it. We sum their weight, like the weight to get there, with the weight of the previous node, if that makes sense. So like, for example, let me snipping tool this. We start by saying this is a weight of 0. Everything else, we'll call that infinity. Actually, I didn't like the way he uses infinity. I'm just going to put a question mark. We don't know. Because this makes it easier to conceptually understand, in my opinion. But just know that he assumes that it's infinite. The idea is like, okay, which nodes near 0, which nodes that are neighboring 0, are the easiest path? And we're like, okay, that would be this edge. 1 is the easiest way to get to a node versus 4. So we're going to go at 1. And we're saying to say, hey, 1, what's your weight? Well, my weight is infinite. Okay, so because it only cost me one, let's call it dollars. We'll say dollars or gas. Yeah. It only took me $1 to get to you. You should say the shortest path to get from 0 to you is $1. So it's okay, this is $1 to get here. And then next we're like, okay, what is the next shortest path from 1 to some other node? We say, okay, 2 is the shortest. 2 is the shortest out of 4 and 2. So we're going to say, hey, 3, how much does it cost for you to get to 0, or to get here from 0? You say, well, I don't really know, so infinite cost. I don't even know if I'm connected to 0 at this point. So, okay, well, I cost $1 to get to me, and it cost me $2 to get to you, so therefore you're going to cost $3 to get there. So essentially we say, hey, 3 is now a cost of $3 to get from 0 to 3. Does this kind of make sense for right now?
Okay, yeah. I'm following.
Okay. And now we look at, here's a strange case. Let's say we're now continue, and we say, okay, the shortest path is 1. And we look at 1, and we say, hey, you take $1 to get to 0. Well, I take $4 to get to you. So therefore, I can't do anything. I shouldn't go this path. You're cheaper to get from 0 to yourself, and it doesn't make sense for me to tell you, hey, you cost $4. So instead, I am not going to look at 1. I'm going to look at the other path, the next best option, and that's going to be 2. And say, hey, 4. It took me $3 to get here, and it takes me another $2 to get to you. So I'm going to tell you, you're $5 to get from 0 to 4. And so you're like, all right. And then you'll notice in the DFS algorithm, we go back, because this has no adjacent neighbors, we're going to go back 1 to 3. And this one, we already looked at all the adjacent neighbors, so we're going to go back 1 to 1. And this one does have another neighbor, So we're going to say, okay, hey 2, it cost me $4 to get to you, and I cost $1, so therefore, in total, we cost $5. And it costs $5 to get from 0 to 2, specifically. And then 2 looks at his neighbors. Hey, I cost $7 to get to you, but you cost $5, so I'm not going to tell you to update. Like, obviously there's some other way to get from 0 to 4 that only costs $5, so it makes no sense to label it as 7. Therefore, we're finished. Or essentially we go backwards. We look at 4 now, and we say, hey, it doesn't make sense to try and label you as $7, so I'm finished. So you can kind of see a basic way of how this algorithm works. But there's a few edge cases. First off, what happens if you have a node outside of this network that you aren't connected to? Let's call this 5. Oh, I'm drawing with a mouse. The reason we label things as like infinite is to say, hey, what is the shortest path from 0 to 5? It's infinite. No matter how many turns or costs, how much money you pay, you can never get to 5. That's why we assume the cost of it is going to be infinite, because there's no way to get from 0 to 5. Or that should be the assumption. Another edge case we have is what happens if we find a cheaper route to 4? Like, what if there was some node, let's say if this was, instead of costing 2 here, it costed 20. In this case, we're going to rewind a little bit. So that means we're going to rewind here, here, here. We're going to rewind here. Yeah. And we're going to say, hey, 4. It cost me $3 to get to me, and it costs $20 to get to you. Therefore, you should be labeled 23. And then he's like, okay, I don't have any neighbors, therefore you go back to 3. We go back to 1, and we're doing the same thing. Hey, 2, it cost me $1 to get to me, and it costs $4 to get to you, therefore you should be cost of 5. And 2 is like, hey, 4, I have a path that only costs 2, and I'm currently 5, therefore that's less than 23, so therefore I should be, instead of $23, you should be $7. And you can see how even if the first value you have at 4 ends up not being the cheapest option, it's okay, because later the DFS algorithm will fix that.
It'll check every edge and make sure you get the lowest one.
Exactly. And there's one last bit of this, is like, what if you have a node that's like, well, there's a couple extra, there's just one more edge case. If you have a negative cost associated with this, you can kind of see where problems may arise. If I say, hey, it costs $2 to go this way, but you'll get back $5 if you go the other way. And then it's like, okay, well, then it cost me $3 here, but then it cost me, I get $5 here. So it's an infinite loop. And theoretically, I could get infinite money. And so you end up having this weird situation where if you have a negative weight associated with something, or a negative cost, you, or more than 2, I think. Anyways, if you have some kind of negative weight, you can end up having infinite cycles. if that makes sense. Does that kind of make sense?
I think so. I mean, it doesn't. I'm trying to see where in the real world application negative getting. How would you earn by still doing?
Yeah, it's weird. It's
It
like
doesn't make sense anyway.
it's the idea that it's an unintuitive concept, but it is still a concept because you're dealing with numbers. You're dealing with
Yep,
numbers,
yeah.
not physical concepts, and therefore you have this theoretical issue where you have a negative cycle or a negatively infinitely looping cycle. Like if it was, I don't know, if for whatever reason a money back guarantee kind of thing, it's like you buy the product for $5, you return the product for, or you buy the product for $5 and you return the product for $5. But then you also could buy the product at a discount for $3. If you don't actually make an edge where it's like you refund the product for a discount of $3, then technically an infinite money glitch would be buy it for discount, return it for full price, buy it at discount, return for full price. You repeat that and you end up being in an infinite cycle.
Mm.
I guess that's one real world example, but even then it's a little stretched. But yeah. Does that make... Are we good on that? On what Dijkstra's algorithm?
Yeah, I got a pretty good gist of it.
Okay. Triple, you good? Do you have any questions on it?
No, I think I'm good.
Okay. Awesome. And like I said, it's a DFS algorithm, and it's made to find the shortest path. Therefore, yes, DFS is the optimal solution in this situation. Next. One other thing this algorithm needs to do, or the shortest path algorithm where you apply how the cheapest option to each thing needs to do, is that it needs to traverse the shortest cost first. It needs to calculate the shortest distance first, or else you get bad situations, if that makes sense. Because if you were to say, okay, the cheapest cost to get from 0 to 1 is $1. But what happens if you go from 0 to 3 and then from 3 to 1? You would be saying that the cost to traverse it is actually no. If you were to say from 0 to 1 is $1, from 0 to 3 is $3, and then you were to say, hey, well, it's a bad analogy. I don't think you can see it in this graph, but trust me when I say that if you aren't traversing the shortest path available in a DFS type of situation, or in the manner you would with DFS, then you'd end up with wonky results.
So if you traverse it with BFS, you would have wonky results?
Yes. Because you're setting costs to things that you don't actually know if they are the cheapest option yet.
Yeah, because you haven't went far enough yet.
Mm-hmm.
Okay, I think it makes sense why it uses DFS, yeah.
Yeah, because DFS is kind of all about finding a cheapest path. And if we just constantly find the cheapest path, we're eventually going to have every cheapest option available to us.
versus with a BFS, which is all about just visiting, checking if each point was visited.
Yeah, it's all about checking if there is a path in general, which is not very helpful when we always want the cheapest solution. It's like, it's kind of like if you're saying, okay, if you need these materials to build this process, and you're like, okay, I need paper, and you're like, okay, well, I can get paper from these 4 stores, and they all have varying prices, and then you're then to go, okay, given each store, this is how much money it should cost to make the project, versus saying, okay, given these 4 stores, this is the cheapest cost, therefore the paper should cost this. Does that kind of make sense? Maybe.
Yeah, I think I got it. It's just understanding that if there exists a path, is with BFS.
Yeah.
Okay.
Okay. Let's see. C. The solution is far away, as in many levels away from the source node. This is depth. This is a depth thing. So essentially it's saying, is DFS good when we have a lot of depth?
No.
Which, yeah, right. With a deep graph, we want to use BFS because it, yeah, we talked about the differences. Essentially, that's when we want to use BFS. And then D, when you're implementing a peer-to-peer network, like a social media networking site where you are attempting to find the degree of connection between 2 individuals. The degree of connection means the number of intermediate friend introductions you need in order to get to the required person. So this is saying, given you know a guy from school, and given your mom, how many connections do you need to get or have to take in order to go from your mom to your friend? It's kind of like a Wikipedia race. Have you ever heard of that?
Yeah,
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 like,
clicking on the fucking links.
yeah. How many links? How many links do you have to go to get from automobiles to France? Right, that's your degree of connection. And with degree of connection, what do you guys think? Do you think?
I don't honestly like. D doesn't really make sense. Like I don't even know what it wants.
So, if I tell you to go from a Wikipedia page on cars, and I want you to go to the Wikipedia page on France, which option do you think is better? If you were to open up every link and then go to each tab that you opened up and open up every one of those links, and you repeat that
Not that one.
process
Not
until
that one.
you find France, or
Just take a link and keep going.
yeah, or do you just go to one link, then another link, then another link? Because you also have to consider this: how many connections can you make? So if you were to, another way of explaining this is like, if you want to go from Arizona to California, should you look at all the connections, or how many flights you can make from Arizona, and then how many flights you can make from the surrounding airports that you can get to from Arizona? Or should you just go from Arizona to, I'm terrible with geography, all the states to the right of it, and keep going down that line until you hit Florida, where you hit a dead end, and then you go backwards slowly, traversing the entire U.S. till you finally get to California? Because DFS is good at traversing every node, but it's not good at traversing them by distance. Kind of like the pandemic one, or the, what is it, the contact tracing question. If you have somebody who gotten sick, you probably want to get in contact with the people who are with them when they were sick, and then getting people who are in contact with those people who are sick, or who were in contact with the sick person. In contrast, you probably don't want to go to the sick person, then go to one of their friends, then want to go to their roommate, who you then go to their friends, their dogs, their brothers, sisters, cousins, dogs, fish, or something like that. But you don't want to just keep extending out on your graph to tell them, hey, you may know somebody who knows somebody who knows somebody who knows somebody who knows somebody who got infected with COVID. Rather, you probably want to say, hey, somebody you know or somebody you're with has contracted COVID. You should probably you should probably stay home for a little bit, and then you contact anybody who they've been in contact with and be like, hey, you may know somebody who may have been in contact with somebody who's got COVID. You might want to quarantine a little bit or something like that. Is that gonna mean it makes sense?
I think it does, yeah.
So with social media networks, it does sound like a lot to do breadth first. However, it is a thorough way of finding, okay, well, out of all the links on the automobiles page, one of those contained a link directly to France. The alternative would be, and then once you find that, like, hey, one of those links had contained France, you don't have to search anywhere else. You know that there is only 1 degree of connection. That is the shortest connection you can make to get to France from automobile. I only have to do 2 clicks and I'm to France. Whereas with DFS, you essentially have to keep track of how many clicks you take on every single link, and you probably will eventually go through all of Wikipedia just to find the fact that you can get there from 2 clicks away. Does that kind of make sense?
Yeah.
Because in theory, you could you could have this situation where, hey, here's France, and here is automobiles, and then here is, I don't know, trucks, and then here is wheels, here's rubber, and here is, I don't know, chemistry. And
Okay.
here, like, you start to see, you probably don't want to go down this route where you have to go all the way to here just to find some French scientist. And rather, you probably want to look at, okay, what is the immediate closest relationship to France? And yeah, so that's kind of why you want to have a breadth first search. We want to look at the most immediate people, and if they're not in that list, then go to the next immediate people until you finally find the closest people to your target. Does that make sense?
Makes sense to me.
Okay. And so the number D, no, sorry, the letter D would be false because you'd want to use, yeah, it would be true. Sorry. It'd be true, or no, false. False because we don't want to use DFS. We want to use BFS. True, false stuff. Weird. Anyways, so recapping, we don't want D. We don't want C. Wait.
Solutions.
You do need, we do want B and we do want A. Yeah. So A and B, I think. But C, far away is deep, deep is BFS, yeah. These two are BFS, these two are DFS. Believe that's right. Are we good? Very lively, I can tell.
So we agree B then.
Yes. B and A.
B and A. Okay.
And yeah, this is being recorded, so you can look back in the recording if you need an explanation on it.
Why?
What?
Wait, quickly, can you go back real quick? Just real quick.
Yeah.
So for A, since it said wide graph, and we said for deep, we don't want DFS.
Yes.
That means for wide, DFS is good.
Yes.
Which is the opposite of deep. Okay.
Because essentially we can have like a connection here, 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 and then we can kind of like make a, yeah. I'm not going to go into further, but yeah, you're right.
Okay, I'm good. Yeah.
9. For the given directed graph, which of the following sequences is not a topological sort? So, I'll recap. Topological sort is essentially saying that the thing should appear before anything that relies upon it. So A should appear before anything that relies on A. So since nothing relies upon A, we can use that anywhere. It doesn't matter where we put this, because nothing relies upon D. Same deal. Because nothing relies upon B, we can put that wherever. However, we have some rules regarding H, G, C, F, and E. H always has to go after B. G has to go after A and B. C has to go after G and before E. F has to go after C and G. And so, looking at this, A, anything with A in the front should be fine. B doesn't have any dependencies, so B works in all of these. H works because it's after B. C does not work because it's not after G, therefore B is wrong. G relies on A and B, therefore it works. So G, same deal here, or goes before A and B, therefore it works here. But C relies on G, and that is before it, therefore it's fine. C, same deal here. E comes before C, therefore that works here. D here is fine where it is. D can go wherever. F should become before C and G, which works. Did I read this wrong somewhere? I thought A and...
I'm not really sure if I understand where D belongs. Doesn't D belong at the very end?
It can go anywhere. Nothing relies on it.
Anywhere?
Therefore,
okay.
We
could have put it at the front?
Yeah.
We're looking for the one that's not a topological sort.
One that's
There's
not
nothing
topological?
connects to
The one
D,
that's
so
not.
it just goes anywhere.
Oh, okay. That's why. So B
So
was
then
the
it
one.
would be B. Yeah.
A and C should both work.
So if nothing's connected to D, so D can just be anywhere along the graph, along the lines.
Yeah,
So like it can be after, middle, before,
exactly.
somewhere in between.
D can be anywhere. If it has no lines attached to it, essentially, or arrows pointing to it, you can assume it has no rules. Therefore, it can go anywhere. If
By
there's
the
a
okay. What if there was like what if there was like another letter, like let's say M connected to D, but it's on the outside, but but there are no arrows connected to D or M. Like
then
As long as then M would go before D, then it would be good.
yeah. So you can think of it kind of like every node has a set of rules that it has to follow.
yeah.
So anytime you see that node, you can check those rules. So anytime you see A, you know it has to be before G. So anywhere here, if G is not after A, then it breaks the topological sort rule. Anything that has an arrow to it, like for instance H, needs to be after what it's pointing to, or being pointed at from. Yeah. So B has to always be before H. So B has to always be before H. And we see that in all three. And where you get tricky is like for something like C, C has three rules. It needs to be after G and before F and E. And when you see this here, it is not after G. It is before E and F, but it is not before G. Therefore, this is not a topological sort because you are listing a node before its dependency. It depends on G and A. Without A and G, then it's not like it's like yeah, it's essentially difficult to provide. I'm gonna stop there before I confuse myself anymore. Does that kind of make
Yeah.
sense?
Yeah, understandable.
It's essentially you want to apply rules to each node, test that rule when you're going through the list, rather than building the topological sort as you go. Because it's easier to just go, okay, is this one passing all of its tests? Well, it's before anything it relies on, so it passes all the tests. You just want to follow that process for each element in the list. If you are going to build the topological sort, one method you can use is you can find the first node that is not being pointed to and start there. So you start from going from A to E, you essentially say, okay, does A have any nodes pointing to it? If it doesn't, then you're going to record that first, and you're essentially going to delete it. And then you traverse ignoring A since we already have it written down. We go to B. B is not relied on by anything, so we're going to write down B. And we're going to essentially erase it from our graph. And then we're going to continue A, B, C. C does have something pointing to it, so we're going to skip over. We go to D. D doesn't have anything pointing to it, so we'll put in D. And then we're going to keep going, A, B, C, D, H. H no longer has anything pointing at it because we erased B. We're going to imagine these lines are invisible now because they were already checked. So we can record H because we already recorded B, so it doesn't break any rules. We continue this process, and we'll eventually get A, B, D, H, G, C, F, and then E. That is I think, which is described in A. Or no, that's not. But that's the idea of a topological sort if you wanted to check for the in degree to see if that's a zero. Which, if you didn't understand what in degree was, in degree is just how many nodes are pointing to it. That's the best way to explain it, in my eyes. Does that kind of make sense? On how you build topological sort, how you kind of tell if something is or is not topologically sorted.
No, I
No,
think I got it.
simple.
Pretty
I'm gonna
simple.
head out. I'm gonna go find some food to eat.
Okay,
I'll see you later.
see it.
Don't start.
Okay, next 10. When using DFS to check for a cycle in a directed graph, can we simply check for the algorithm visiting a marked node? So
Um. So, checking to see a mark. Actually, I'm having a hard time visualizing it. So let's say you did have like two children and you've already visited both of them.
mhm.
Wait, is it asking if it's a directed? Okay. It has to be direct.
Yes. I would say no. The reason being is one, I remember this problem in class. Two, when you're trying to check for a cycle, you're essentially trying to check of whether or not this node has been marked on the path we're currently traversing. So for example, if we have a path to get from A to G to C to F, if we then also have a path from like A to H, and we went H to G, at first, A may go to H, mark G off and say, okay, whatever. And then A is going to then look again and see, oh, G is already marked, and assume, oh, it's a cycle. It must be a cycle, even though there's no way for G to get to A.
Mm-hmm.
So instead, what you do is when you're keeping track of like what nodes you still need to look at, so like when you have your stack of like A to then G or to H, and then G, you're essentially keeping a list of the nodes you took to get to here. And if you ended up having something like, I don't know, E connected to G, you'd end up with like C, E, and then you'd be like, okay, is G inside of my stack? Yes, it is. Therefore, there must be a cycle here. Because I can go
Alright.
from G to something to back to G.
While still exploring in the initial.
Yeah. While we're exploring some path, we managed to get back to one of the nodes we took to get here. Does that kind of make sense? It's kind of like if you're on a hike and you have a bunch of split paths and you want to make sure you don't go in circles. Every time you have to make a decision of where to turn, you place down a rock. Every time you reach a dead end and go back to that intersection, you pick up the rock. You pick up the rock at the end of that dead end. And if you ever find a route that lets you go back to a spot with a rock, then you know you've gone in a circle. Does that kind of make sense? I don't know if that made it more
So
confusing.
basically, let me try to word this right. So basically, there could be multiple paths to visit that same node, and if that node is already marked, it would assume that it would be a cycle, which is not true.
Mm-hmm.
Is it? I think does that sound right?
Yeah. Just because it's marked does not mean it's a cycle. It's only a cycle if it's marked and it's on the current path we are immediately on. Because like if you remember, DFS kind of builds a path as it's going. Like it goes from, Like when you're traversing DFS, you kind of build a path of where you're currently looking at, and once you reach a dead end, you kind of erase and you go back, and you kind of erase, kind of in this pattern. And sure, you've already looked at F, but you don't really care whether or not it's marked or not. You're really caring about whether or not there's an arrow to get to F already, if that makes sense. Or if we've gone paths there already. I don't know if that didn't sound too well, but did I answer your question? Or confirm it? Triple?
Yeah, no, I think it should be good.
Okay. Okay. So, yeah. That was 10. The rest is, okay. Programming, binary search trees. On the real exam, there could be a programming question on BSDs, hash tables, or graphs. One of the data structures we studied is a binary search tree. A simple implementation of a node for a binary tree is shown below. For this question, you are to implement a method called isBST that takes the first node in a binary tree, its root, and returns true if it is the root of a BST, false otherwise. Please be careful of the syntax. So I'm going to throw this into here. Okay, I'm just going to rewrite this. We'll call this, oh wait, I see. Okay. Okay. And we're going to have public boolean is BST. This extends. Oh. GitHub Copilot trying to make a suggestion. Anyways, so this is our setup. We essentially want to, check if it is the root of a BST and false otherwise. So first off, we want to check whether or not the root is a binary search tree. What do you think the first step of this is?
Check if it exists.
Okay. So we check if it's null. If it is, then return false. Right. What next? What's next? So we have some tree. Like this. Okay. You have some tree and saying this node right here. We first want to check, okay, is it null? It's not null? Okay. What next? We want to know if it's
If
BSD.
the left's
Yeah, continue. Sorry.
maybe call like x.left and have it compared to the root. So if the left side is less than the root, so like compared to that, and then you can compare the right side and see if the right side is greater than the root.
So you're saying int compare equals root dot left. Something like that.
Yeah.
Okay. And actually, we should probably compare ourselves with our left and right first, right? Bless you.
Thank you.
Compare our roots to the left and right children, right? And our right comparison. Essentially, we're saying, okay, we want to check first whether or not this number is, let's call it 5. If this is greater than it, or is less than this, are we doing greater than or less than? I can't remember. This is less than, right? Left is left. So let's say we want to make sure this is less and this is greater. That's the first thing we should check, right? Or second thing.
Yeah.
So we want to say if the left comparison is what is it? Compare to is, oh, this is going to be confusing. Okay. Okay. So if the left comparison is less than 0, or the right comparison is greater than 0. So essentially saying if 5 is less than 2, and we're on the left, we're talking about the left, then we want to say, no, this isn't correct. And alternatively, if 5 is greater than 6, we want to say, no, this isn't correct as well. Does that make sense?
Yeah.
Turn false. And then we're then going to stop giving the hints. Okay. Next thing we want to do is what?
I think a little bit of recursion happens, right?
And how so?
You call.
So if it's recursive, it means it's probably going to call is BST, right?
Yeah, so you call it self, and then you call the node dot left. Well, the root dot left, and then you call the root dot right.
Okay.
Is BST.
And what do you do with that?
Sorry, I'm
wait.
just not too good with recursion.
Oh, I think we forgot one step. Check if no, step 2. Check if the left or right node exists.
Oh yeah, check if the left or right exist.
Oh, it caught on to what we were doing. So, check if the right node exists, and then okay, and then if they're not null, oh, we should probably left is BST, right is BST, and okay, so we were checking if the left exists, and if it does, we want to make sure that the left is less than our root node, and if it is less than our root node, we want to then recursively check if that left node is a BST. So left is a BST equals is left root dot left. Then we apply step 4 recursively check. Yeah. Step 5, check this. Actually,
I think flip that greater than sign. Right.
what?
Oh, in your if statement, not equal null. I think it's supposed to be the other way around, right? The if root left key compared to.
Yes, I think this also works if
Or
I'll try it with the other way around just because, yeah. There. As long as you swap the greater than or equal to sign, I think it should be fine. They're just inverse properties. Yeah. There. Return false. I don't like the curly brackets. And then we are going to recursively check the right node is thing, and then we return if the right is not a BST, we're going to return false. But if those are true, then we know it's a BST. Alternatively, we can just simplify that to return right as BST. Does that make sense? Maybe? Do you have any questions on that?
it doesn't matter which one you're returning, right? You can call left is BST or right is BST on the bottom.
On the bottom?
Yeah.
Like right here?
Yeah. What if it was like returning left is BST? Is that still the same thing?
No, because assuming if left is BST is true, then this is going to be true. So if for example, if I were to put that in here,
Oh, is that still inside the if loop?
you can
The bottom?
you can see IntelliJ is warning me like, hey, the value of this is always true because of this statement. Because anytime left is BST is false, aka anytime the left side is not a BST, when we check it and return false, we essentially say this code can never be run if this is false. Does that make sense?
Okay, yeah. I
Because
see.
it'll suggest, oh, you want me to just simplify that to true? Since it's always true? Or instead, we need to do right as BST, because we didn't actually do anything with this value. We just said, okay, is the right a binary search tree? If it is, then we should return whether or not it is. But beforehand, if I just had this, or if I just had this, it's essentially saying like, okay, is right a BST? I don't care. I'm just going to return true. Which is not what we want. Another way you could do this is this, but again, it's like this is always true, so it's redundant. So you end up just being better off doing this. Does that maybe make sense?
No, that makes sense.
Okay. Awesome. That
Are
would
you gonna
be...
post that code in the chat too, or is it
Yeah,
gonna
I can.
be? Okay.
Actually, I'll have GitHub Copilot generate some examples. This should not be private, this should be public. Create a binary search tree. Come on. Oh. You don't care about size. You know, it does have it there, but actually,
Wait, does IntelliJ automatically create a constructor for you?
no, this isn't the, yeah, it can. It can
Huh.
generate constructor. There. Or if you want to generate constructor with only key and value.
Damn, I have not been using IntelliJ to the fullest.
And then we can go check if the tree is BST. Not, is, oh, wait, public static. Let's see. This might have a problem. False. Let's actually visualize this. So the root is A with a key value of 1. The right is 3. Left is 2. And then if we go on the left of that, the left of it is 4. So yeah, there's an invalid node right here, which is why it's not a valid BST. But if I were to go and check, hey, is, I don't know, is H a valid BST? If I were to go check if H is a valid BST. It should be true because it has no children. Now, a balanced binary search tree. Instead of string, I'll do character. There. Let's see if that works now. Wait. Add. I don't know if that's valid necessarily. No, it probably isn't. Anyways. You guys can probably see if this works on your own time if you want. You can play around with it. I'm not gonna try and spend too much time on this. Probably spent way too much time on this in general. Let me post that in no mic. I'll post it in no mic. Actually, I can probably upload it to Pastebin. I'll put it in the video. There. Something like that. Anyways. Continuing. The next part is undirected graphs. Sorry about taking too long. So run the BFS algorithm on this graph to compute the shortest paths between 0 and every other node. For reference, the BFS algorithm is shown below. Use the adjacency list above for the order of the nodes explored, and follow the trace format shown below. Your answer must include the values of V, Q, and edge 2 as they update. Let's see. Is this one of those? I guess it's not a directed graph, so that's why. Okay. Let me quickly replicate this. Oh, wait. Oh wait, it's a boolean. Alright, marked S equals true. Q add S while Q isn't empty and V equals Q remove, and that. Edge to WV. Okay. Oh, this is an algorithm trace. I thought it was a programming problem. I'm dumb. I apologize for that. Okay. So, we're starting from which number? So from 0. So we start off, and our first thing that's marked is going to be... Wait, are we starting at 0? Yeah. Oh yeah, 0. The first thing we're going to mark is 0. And then in our queue, we're going to queue up 3 and 1. So... Let me... Alright. So before we start, we're going to first label 0 as marked. 0 is going to be marked, and our queue is going to contain a 3 and a 1. Right? And first go around, our V is going to be our 0. Oh, wait, our Q is going to actually be just 0. My bad. Why is this so tiny? Okay. The Q is just 0. Actually, let me ask some of you guys. What do you think I should do first?
0, I think. Oh, no.
No, go ahead.
So at 0, you mark it to be true, right? So you said mark 0 true, and you set the queue to be 3 and 1.
Yes. In our loop 1, right?
Oh, that's in our. Oh, I thought it was before.
Yeah, I
But
accidentally did that. My bad.
no. In our loop 1, we would be at v equals 1, right?
I think I messed you up at the start, so I apologize. So the first thing in our before loop is what's happening right here. We have an empty queue. We mark the number we're trying to look the search from, which is 0, as marked, and then we add that node into the queue. So the only thing in our queue is going to be 0, and the only thing marked is going to be 0. Then we start on loop 1. So my apologies.
So you marked 0 to be true, and queue. No, the only thing in the queue is 0.
Mm-hmm.
Okay.
So what do we do next?
In our next loop, v would equals to 1, and since 0 is already marked, you add.
I mean in
you
loop
do
1.
edge. Oh yeah, so you do edge to 1 to 2, and then edge to 1 to 3, and then you add those, and you add 1, 2, and 3 onto the queue.
Can I ask you why you started with 1?
Isn't it? Are you incrementing it by 1? Going plus 0. Well, not incrementing, but like 0 is connected to 1, so.
Every time we loop, we're going to take what's in the queue and set that equal to v, right?
Oh, okay.
So, because if you look right here, while the queue isn't empty, so while we still have stuff in the queue, which if we look, we have something in the queue, we have 0. We're going to take that element and remove it. So we're going to remove 0 from the queue, like that. And now v equals that queue. So, or v equals 0. Now,
Okay.
the inside of our for loop, we're going to go through all the adjacent nodes, W, and we're going to check if any of them are marked. So like 1 and 3, because none of them were marked, we're then going to say, hey, make an edge from 1 to 0. We're going to say, hey, there's an edge from 1 to 0 here. And we're going to mark it. And we're going to add all of its neighbors. Well, actually, no. We're going to add that to the queue. So we end up having 1 in the queue. Next up.
Why wouldn't we go to 3 first?
Because we haven't gotten to 3 yet. 3 is actually next. 3 would be, we're going to say, okay, 3 is an adjacent to 0 as well. Therefore, and 3 is not marked. So 3 now points to 0 and with the edge 2. And then we're going to mark 3 and we're going to add 3 to the queue.
Question to that. What if
Sure.
you just do it the other way around? What if it went 3 and 1? Or does it not matter the order it was in? Or
I thought we were supposed to go in the order of the table given. So like 0's adjacencies are 3 and 1. So I thought you went to 3 first.
Oh, I forgot about the table. So yeah. So you would do 3 then 1. My bad. I didn't see the table was out of order. I assumed it was in order. Well, yeah. So, yeah, first you'd look at 3, which would be edge from 3 to 0, and then you mark it, and then you add it to the queue, and then 1 has an edge to 0, like that, you mark it, and you add its neighbors to there, or you add it to the queue, I meant. And I believe the first thing we look at is 3 next, the next loop cycle. I can't remember if the queue is...
Depends on where the front is.
Mm-hmm.
Front of the queue, I'm assuming, is the left. Sometimes he makes it the right.
I think this is a first in, last out.
But the queue?
think
The queue
you
is
can-
first in, first out, but
Oh, is it
no, I think you
FIFO?
pop it from the front and then you add it to the back. Right?
which is a queue, which is first
Yeah.
in, first out.
Okay, so it's first in, first out. That means like 3 is, yeah. 3 is the first one we're going to look at. So we're going to look at 3. Why did I have a bigger one? Oh,
Damn, has it been 3 hours? Oh.
yeah. Sorry about that. I think it's probably been 4. Or no, 3, I think. We'll see. Wait, actually, OBS. Yeah, it's been 3 hours. Oof. I can try and hurry it up. Okay. You take out 3. V now equals 3. And then we say all the adjacent things. 1 is already marked, so ignore it.
We have 0 and 4.
Yeah, 0 is already marked. 4 is not marked, therefore 4 has an edge to 3, and it's marked. And then we add 4 on to here. Yeah, I'm just going to cross out the numbers from now on. Now we continue on to 1. 1, we look at its neighbors, we see, okay, 0, which is marked, 4, which is also marked, 3, which is also marked, 2 is not marked, therefore 2 has an edge to 1, and we mark it, and we add 2 to the end, and then now we're on to 4, v equals 4, and 4, we look at 1, which is already marked, 3, which is already marked, and then 5, which is not marked, so therefore edge from 5 to 4 marked off, and then add 5 to the list. And then we look at 2, 2 has nothing, therefore we get rid of it and we skip. 5, 5 is nothing, therefore we're done. Sorry, is that Yeah. Does that make sense?
Yeah, I think I followed. It was like the one we did
In class.
in one of the short answers. Yeah.
Oh, that too. Yeah. It should be relatively simple. I guess if he gives you something like this, yeah, use that as the ordering. I was assuming the order was sorted.
1, 2, 3. You mean?
Yeah.
All right.
Yeah, in order.
Yeah, I guess.
Then we have the extra questions. Do you want me to go to the extra questions as well?
Um,
Honestly,
extra
why not?
questions are just
Actually, let's see. Let me.
they may use content covered. So basically saying that the content might be in the test, but the questions won't be. Questions.
Following
Basically,
question
should
were
we have
used
to
on
Now it
previous
says
prep.
previous exams though, so something
Yeah,
very
content.
Amazing.
Use separate lines for each key pair. So tracing a hash table?
A
Is that what
binary
it is?
search tree.
Oh no, binary search tree.
So you're essentially,
Oh, so you're just drawing a tree.
yeah. Yeah. You're drawing a tree here. I don't think we need to go over that. Consider the task of implementing a symbol table versus an ordered symbol table for the purposes of get and put. Which,
Wait, hold on, wait a minute. For the first one, so 150, 150, 100, 100, they both have the same integer value.
yes,
So
they're not
like,
keys. This is the key, this is the value. The keys must be unique. The values do not need to be.
okay, so CSE 110 would be
Mhm.
less than 205, so 205 would be the root then, right?
I think
Or
depends on how we're
it depends on the
like how we're
ordering
in
and
the
how you.
binary search tree.
It depends on the hash function. Not the hash function.
Also,
The
it doesn't
keys.
tell us how to sort the binary search tree.
Yes, that's the other thing. We don't know how to sort the binary search tree. So you could assume that you're doing it alphabetically. I would assume, and then you're essentially making a binary search tree, but instead of comparing like is A less than B, you're essentially saying is this thing alphabetically before this thing. And like if you were to sort this in alphabetical order, you have CSE 110, 205, 230, then you have SER 316 in alphabetical order.
oh yeah, use
Oh, I
ABC
see.
format. Okay. Hmm.
Um,
I see. We're not using integers to say like, oh, it's less than or greater than. Rather, we're using the numbers in the string.
Yeah, you're using the entire string. If you think about it, you can compare strings and get a -1, a 0, or 1, depending on whether or not they're quote unquote less
Wait.
than.
What if they're using the same letters like CSC 205, CSC 205?
You're updating the value then. So that's one thing about
Oh, the value's
table.
getting updated.
Yeah.
Okay.
Usually with symbol tables, when you say put this key comma value and you reuse that key, you're not assuming there's two separate things. You're assuming, hey, update this thing. Kind of like how you have a grade book. It's like put in B for this person's name, and then later you're like, okay, put an A for this person's name. You're updating that value. You're not saying, okay, there should be two people with this name and they should have different grades. Does that kind of make sense?
Yeah, I got it.
Yeah, I'm assuming you can draw this out to some extent.
Yeah.
2. The task of implementing a symbol table versus an ordered symbol table for the purposes of get and put, which you would be we should be more likely to create an efficient implementation for. Which should you make an efficient implementation for when it comes to symbol table and ordered symbol table? Okay. No knowledge of BSTs or hash tables is needed is the hint. So with a symbol table, do you care more about how much time it takes to get something or how much time it takes to put something in there? What do you guys think?
You be more implementation. I think put.
Put for a symbol table? That's what you're saying?
Yeah.
So you're saying if you want to, like, which one needs to be faster for a symbol table? You think put. So get can have a little bit of time delay. It can, we don't care. It can take a little bit of time to get something from a symbol table versus an ordered symbol table. Or are we saying, well, actually, let me go through my thought process and then see if there's a hole in that logic. My thought process is, when you add something to an ordered symbol table, you're okay with having a little bit of performance-ish or impact. Oh wait. You're more likely to make an efficient implementation for an ordered symbol table versus a normal symbol table when it comes to put, I think. Because if you aren't careful, you might have, when you have to keep order in something, you have to, well, okay. In a symbol table, you don't care about where items are placed as long as they're consistent when you do get and put. And therefore, it's not as bad for getting and putting, whereas with an ordered symbol table, if you can imagine it, if you're getting some item from a ranking of all the best schools in the world or something, you probably don't want to take a very long time to check that those schools are in order, but rather you want to make sure it's ordered when you put it in, right? You essentially want to sort when you place new items inside rather than sorting when you retrieve them. Does that make sense? Maybe.
So you're preferring get over put. You're doing the get method than the put.
Yeah, you essentially want to make sure that your get is fast, like as fast as possible and consistent, but your put may be a little costly. It may be a little costly to add things to your ordered symbol table, but as a result, it makes it much faster to get something. With the normal symbol table, you just want speed in the first place, because you want to be able to get things fast and put things in fast. Since order doesn't matter, you can place it wherever it fits, essentially, as long as you can get it out quickly. That's how I think of it. I'm not entirely sure if that's what it's hinting at, or what it's wanting you to get at. Do you guys have any comments on that?
You said something about the order symbol table. You want your get to be faster than your put.
Yes. Like, if you think of it like a trade-off, when do you think you should spend more time doing something? When you're adding something to a list or when you're trying to get that thing from a list?
I'll be adding.
Yeah, exactly. Because you only have to add things once. You have to get them potentially infinite number of times, right? for example, like Google, you're constantly having to search things, but that doesn't necessarily you're constantly having to add new websites. I mean, yes, when you scale up super large, but relatively speaking, you probably search more things than you probably search for websites more often than you do add new websites to Google search engine, and therefore
Think
it's
about your upload speed and your download speed.
yeah, like you don't need to upload things as much as you do download. It's another analogy. I don't know. Did that kind of answer the question? It's like symbol table, you kind of want to quick get and put, but ordered symbol table, it's okay to have less efficient implementations for put in favor of making get very efficient. Okay. And this, if we're referring to binary search trees, this is like the login versus, what is it, nlogin? It's nlogin to put things in and sort them. It's login to get things. Okay. For 3. When adding and removing nodes from a heap, the tree structure will always remain balanced. Why is it the case that when these operations are performed over a BST, there is a chance that the tree will become unbalanced? In a BST, there's exactly one place in a node may be added. B, in a BST, nodes are always placed in the level nearest to the root node. C, because heaps use an array while BSTs use a linked node structure. And D, this is a trick question, both BSTs and heaps are always balanced. What do you think?
Not sure.
I think it's D.
Deleting it. I think it's D.
Yes. Because if we look at balanced,
Dog.
is it hold up. There's a full binary tree, which is every node has at most 2 nodes, or either has no children or 2 children. A perfect binary tree is one that has equal number of levels. It's like a, it looks perfect, You can see that. Complete is everything, all leaves elements lean towards left, yeah. Yeah, it's not, I don't think we really talk about complete binary trees. A balanced tree is, balanced tree is just that the depths match up. The depths are no larger than 1 or 2. So I wouldn't say D, actually. I messed up with that. And I wouldn't say C, because linked node structure doesn't really mean anything.
I don't think it matters for C if it's an array or linked node structure.
Yeah.
So I don't think C is right.
Mm-hmm. Yes. Okay. So with I think it's A. The reason for that is with a heap, the only things we care about is mainly that the top and the bottom levels the top, or for example, a max heap, we only really care that the top is a maximum value. We don't really care too much about the rest of the tree, or the rest of the heap. With a BST, we need to ensure that there's left is less than, right is greater than, which means that removing a node means that every other node needs to be adjusted, and or moving a node in general, it needs to move to a specific place. Meaning there's only one place it can be added, or should be added. And balanced, I mean, a balanced BST. Reason why it's not B is that we don't always place BST nodes in the level nearest to the root node. This just doesn't make much sense. And then D, we showed that it's not the trick question, because I think he was just talking about, is it a binary tree, or is it a tree, I guess. Oh wait, is he talking about BST or balanced tree?
Wait. So to understand the difference between the heap and the BST, heap is just the set of rules, and the BST is just the structure of the tree, right?
A heap is
It's like it has to be like if it's a max heap or if it's a min heap, and a BST is just like the tree structure. Well, just the tree.
yeah, a heap is more like you have some rule specifically to the root. Where the BST, the binary search tree, is you have some rule for the entire tree. So if you were to take any node in a BST, you can make a BST from that node, as we showed in an assignment we were programming earlier. If we were to take any node in a max heap or min heap, we could not make a max or min heap directly from that without having to change a few things. Does that make sense?
Okay.
I do think, yeah, BSTs, I do want to argue though, wait, both binary search trees and heaps are always balanced. I wouldn't say balanced, no. Yeah, no. No, because like a max heap where you just keep adding numbers that are larger, you'll end up creating a large amount of space, because you end up having like a stilted tree, aka like a node connected to a node, like something like this, where you just have them all connected like that, which is not balanced. Balance would be like breaking this, choosing this as the root, and then moving this down to here, wherever. Actually, that works. Okay. But yeah, this would be balanced, but this is not. Anyways, essentially A is what we're choosing. And then, okay, we're almost done. 4. If you are asked to run a BFS or DFS, or DFS or BFS by hand, and given a picture of the graph and the code for the algorithm, why is there a chance you and a classmate who correctly execute the algorithm will produce different paths? What do you
What?
think?
If you're asked to run by
By hand.
um I guess like maybe so far in class we've always assumed that you would go in order.
Mm-hmm.
So like, if you're on node 5 and your adjacent nodes are like 1 and 3, right? You're gonna choose 1 just because it's in order and it's not indicated like otherwise specifically. So, I mean, if you stick to that, you should actually get the same path, which is why I'm kind of confused.
Well, let's assume
But
you
if
didn't.
that's not given,
Yeah, I think that's where
then
the problem lies.
go into different children.
Yeah, that affects DFS, and same with I guess BFS as well. Well,
It does because I
well,
mean you're gonna have to
well,
go into one
yeah,
eventually.
yeah, I see what you're saying. Yeah, it would be. It would affect if you don't have a quote unquote in order to follow. I would have said arguably if you start at different points, but I think that's semantics. I think that's like an edge
Oh
case
yeah,
thing.
that too. But yeah, so far in class we've always assumed we start from like either like the top or the in order,
Mm-hmm.
like usually from 0.
Mm-hmm. Yeah, I definitely think
I'd
it's
probably state that in the answer, like assuming this.
yeah. It's always great to put more information about what you assumed. If you make any assumption at all with these questions, write down the assumption. Because that's the difference where they're like, well, I don't really know if you understand it or if you do. As well as it kind of explains, like, okay, where did this student come up with the idea that you could get different graphs? Well, the fact that they talked about you could start from different points, making different paths, obviously. Or that you don't necessarily know that there is an order. Therefore, that's how you can get a different class. Explaining how you arrive at that conclusion is extremely important on getting like full points in these problems. Kind of like showing your work, but showing your assumptions. Okay, are we good on that?
Yeah.
Okay, last one. And in the DFS based topological sort, what would happen if nodes were pushed onto the stack before their children were explored, rather than after? Would the algorithm still work? Explain. What do you think?
They would just, well, wouldn't there just be like too much work done for no reason? But like still technically work?
I'd argue nothing changes. Oh wait, DFS based topological sort. Well, I just see it like this. DFS already is using a stack, right?
Yep.
Therefore, pushing all the nodes to a stack is the same as recursively calling. Although I think
Oh, I see what you're saying. In a stack or a queue?
stack. Because if you remember recursion, like when you have too much recursion, you have a stack overflow error. Meaning recursive calls use a stack of in regards to like how they traverse. The only difference between DFS and BFS is whether or not you use a stack or a queue. That's literally how you can change the algorithm. If you implement them, you can have the same exact implementation, and depending on whether you give them a stack or a queue, will determine whether or not you're doing BFS or DFS. Does that make any sense?
I think so.
Okay. I have a train behind me. Again.
There's a train.
There's a train right behind my apartment.
Oh, I thought. Oh, I thought you said there was like a training dog.
Oh,
Bro.
no. Sorry.
Bro, now I'm so lost. Okay.
That's the
You literally
choo-choo
said a
train.
train. Okay.
Yeah. I'm trying to think of how this changes for topological sort. Let me look at module 12's topological sort. We already run DFS. Yeah. I mean, I guess it would just become iterative. I don't know. He already implements a topological sort with DFS where all the nodes are pushed onto a stack beforehand. That's literally what we're doing here. And we just reverse it. I'm just trying to think about this. What do you guys think?
I'm a little bit stuck on this one.
Same.
I don't know.
I
Okay,
wanna say
so
I'll still have to work though, right? Because if you were pushing out or explored.
it's just gonna be extra work.
Yeah, that's why I think too. There's just gonna be more work.
I guess. I just know where the topological sort comes in. Why did he say topological sort, not just running DFS?
Don't we
So-
normally push them before instead of after? I'm confused.
Yeah, that's what I mean.
Okay.
That's what we normally do, is the thing. And he did mention this is from different exam years. It's either, I think of two possibilities. A, these are slides, or these are questions from slides that he eventually changed, so he probably switched it from DFS based to BFS, maybe. Or,
You forgot about it.
or it has something to do with topological sort. Or, yeah, he forgot about it. My thought process is like, maybe because, I don't know, thinking something about with the path being built, but I mentally cannot imagine that being a problem. So I'm not sure.
Here, look at the picture I put in general.
Alright.
So you're putting. This is how you do topological sort on the slides.
Mm-hmm.
You push your vertex to the reverse post at the end.
Mm-hmm.
I think he's saying, why don't you do it before you do the depth first search?
Oh.
like before that if.
Huh. Hmm. Well, because you'd have duplicates? Well, no.
Oh, I see.
No, I think it'll still have to work then. If it's reverse.
That'll still
But
work.
it depends on if the DFS has anything to do with V itself, and it doesn't.
Yeah. Reverse push has nothing, and there's no like return statement anywhere here, so therefore it has literally no effect. Because anytime DFS is called, oh wait, no, it does. It does. It does have an
Because
effect.
it's recursive and it.
Yeah.
Okay.
Because it waits to finish at the end. Yeah. It would
It
have
would
an
use
effect,
V.
but whether or not that matters.
Back-
What was that? You lagged out.
Yeah. Normally you push them on when you bubble up, and now you're pushing them down as you go down. Push them on. So the ones that are at the beginning will be at the end. Like when you print them out, it'll be backwards. It'll read from right
Reversed.
to left instead of left to
Okay.
right.
So it'll be reversed, which is good.
Yeah.
So it's a good thing.
Well, it's a
Because-
different thing.
Oh wait. Oh, reverse post does not mean to reverse the order. That just means get the reverse. Okay, so it'd be in reverse order.
Yeah,
We-
so the things that are. So we usually have the things that are less dependent first. So we would have the opposite.
Mm-hmm. We'd essentially have the dependencies backwards. Where we'd start with the most dependent thing and end with the least dependent thing.
Yeah.
Okay. Alright. That should be it. So any other things you want me to go over? Or we should go over now? Module 9, 10, 11, or 12? Any concepts you're unclear with? Anything like that?
Hmm. Even if there are, my brain is like exploding mode.
Fair. um,
That did cover a lot of this stuff, though.
yeah. Do you want me to go over anything programming wise? Like how to use IntelliJ or anything like that? It's got a lot of cool stuff.
If it's not on the test, I ain't worrying about it, bro.
I don't know if you noticed the text suggestion thing. That was like this. The
Oh yeah,
creating
that
your
was.
study. Or a better example, I think, was I don't have it here. I do not. But if I were to have like, if I were to make a class like binary search tree, and I were to just, I'm only pressing enter and tab.
Okay. All right.
Does everything for you?
That's cheating, bro.
Wait.
This
Hold
is the
up.
type
How?
of.
Are you just?
Bro, this is what I needed when I was doing the assignments, bro.
I
Wait,
can't
hold
condone
up.
using it for assignments, but it is, as you can see, it's not perfect, right? It messed up the syntax here. However,
I'd submit that.
you can see very much like things that are done. It's very good with helping you code. So if you're like, if you have a method called like public static, I don't know, I get height, and you're like, okay, I've done this method or whatever. I'm like, I want to document it, so it gets the height of the tree, and it has a parameter root, the root of the tree, and maybe it throws an error, like throws the argument exception, and if the root is null or something, like things of that nature. Like, it's useful for comments. You can't just copy and paste majority of the code. You have to do some thinking. An example of which is like, I was trying to do, I don't know, sorting algorithm. I was trying to do like perform an iterative quick sort on an integer array. And you can see it doesn't really understand the fact that I said iterative. It immediately tried to do recursion. See, it's back to doing recursion. However, it does understand that the quicksort algorithm in the first place. So it does know how to do like a quicksort. It also will know how to do a merge sort.
Somewhere?
It's an AI, so it's trained on GitHub, like on a bunch of just different GitHub repositories, and therefore things that have been done over and over and over again are very easy for this thing to figure out. Like the fact that I was writing binary search tree, it has a node that's the root and a size, and it was able to come up with all that on its own. Like it's
Damn,
done
so
it
this
all
is like
before.
a double-edged sword here.
Yeah. Like it can be very helpful for things that are just repetitive and annoying. However, it is not good at new solutions. Obviously, it's better for something that's just like you're doing a lot of documentation, you're doing a lot of grunt work, you're filling out a bunch of classes that are probably pretty easy, maybe like a few lines of code, or you're doing simple if statements, like things like this, or simple for loops. It can be very helpful in that regard, but you do need to understand what's happening. Otherwise, you end up with weird issues, like, for example, this. I just say, hey, do an iterative quicksort. And it's like, okay, let me do a recursive one for you, which is not what I told it. But it is very useful. I did this, I think, if I do a new project from version control, if I find my the multi-threading examples, clone that. Okay, project structure. Right now it doesn't know what Java version to use, and so I'm defining that, saying, hey, use Java version 17, and you'll see.
Wait. So I never got these. So I never used GitHub before. So is it just like a place for you to like store code and look at other people's code in a way?
Yeah. If I go
I really gotta
to
learn to use GitHub.
your profile, you have repositories that these are each different projects that I've either helped, that I've either made, worked on, or favorited. And for example, the one I was just showing is this one. You can see it. I don't have like a README file, but that would make it easy to read. You can kind of traverse my code in browser. You can see what I'm doing here. Exact same. Why is it being a pain? And it's being a pain right now. Is it modules? Yeah, it's an indexing problem. Sorry about that. Sometimes projects just like to complain. There. All I did was, it was saying, hey, I don't know where this file is, I don't know where this folder is, I'm going to complain at you. And what I said is, okay, let me make a new folder, or a new package, and move everything to that. So like, hey, I see this file, it's now in a package I know of. I'm like, okay, what if I move it back? Oh, I know this package now. And it fixes itself. Jank solutions, but you can see I have a bunch of sorting algorithms, which all these were generated by GitHub Copilot. So selection sort, insertion sort, bubble sort, quick sort, partition or shell sort, radix sort, counting sort, heap sort, merge sort, anything that, all these were generated. Except for the iterative quick sort. This is what I had to make myself. Bubble sort as well. And then what I'm doing is I have a main class where I generate a bunch of random integers right here, which I also have sequential data if I need. And then I clone it a bunch of times, just so that each one has their own array to sort. And then I make a new, make the new elementary sorting class so I have access to these algorithms. And then I make a new benchmarking thread, which it's a little complicated. Just think of this as like, this is a program that takes an algorithm and some set of data and runs the algorithm on that data. And then from that, I made a benchmarking version of that where I take the data, the algorithm, and I name, and then I time how long it takes for me to run that algorithm. And then when it's finished, I say that it's finished and the program ends. Then I have another thing called thread race. This takes a series of threads, and then it prints 3, 2, 1 race. It starts all the threads and it checks all the threads every 5 seconds to see if they're still alive. If they haven't, essentially to see if they're finished or not. And if they're still alive, it prints out the name of it. And then if it's not, if all the threads are not alive, then it says all threads are finished and it finishes. My main is essentially just making a bunch of these selection sort algorithms, and you can see this would be very tedious to write by hand. I think you guys can all agree this looks very tedious to write. You'd not want to write this on an exam, of all places, where you'd have to write this out by hand.
No. How about no?
Exactly. And so, essentially, GitHub Copilot can recognize, hey, you've been doing a lot of this where you've been doing somewhat of this pattern, so I'll just help you out by suggesting, based on this file, what are the sorting algorithms you haven't done. So it makes grunt work a little easier. And then what I do is I do a new thread called race, and it's my new thread race with selection sort, search sort, bubble sort. All these are threads. And then I print out, let's benchmark the performance. And then I print out how many elements there are, and then I start them. And you can see an array size of 1,000 elements. It takes merge sort 7 milliseconds. Heap sort is 13 milliseconds. Java's sorting algorithms are pretty jank, and so they'll just throw an error. Shell sort is 19. Quick sort is 25. Iterative quick sort is 27. Selection sort was 203. You can see all the times that each algorithm took to run, which this kind of lines up. Merge sort was pretty fast, as we learned. Like heap sort was pretty good. Insertion sort is bad on iterative data, but shell sort is a little faster because it kind of partial sorts. Quick sort is quick, not as quick, but pretty quick. Bubble sort is pretty slow, slower than selection sort. But yeah, you can kind of see that example, and you can also see like worst case scenario for like when you have a sequential data that is in order. You can see that insertion sort is the fastest, just because it only goes through once. Selection sort takes about the same time as it used to, and it did before. Java sometimes likes to hang, because Java's just, it's the problem child of the group. It's not the smartest. Oh yeah, the other Java sort ended up throwing an error. But I don't know. I find this stuff a little cool. I'm just kind of messing around with threads. Oh yeah, I have also mentioned. Oh yeah, insertion sort is the slowest when you have the worst case, which is when they're no longer ascending, they're descending. I don't know if you recognize this thing, this var. Java, you can do this if you have a function that returns some kind of known data type, like integer array. You just put var here, and your IDE will figure it out for you. Same with Java itself. It'll fix it and put integer brackets. It's just a really good shorthand if you ever need it. I find it really helpful. Because I can just go like, boop, boop. I don't care about the types.
I'm gonna head out again. Thanks for running the review, Hunter.
Yeah, no problem.
Yeah, thank you. It's
I'm gonna head out too.
Right.
Thanks, man.
I'll probably stop it there then.